So hello, everyone. Welcome to the session. We would like to invite all of you to write in the chat, as Thomas is doing, to say hello, say where you're coming from, where are you connecting from. Good to know, because we are morning and evening, so it's good to know where we are all. And then feel free to share also how's the weather like in your place and how you're experiencing it. So today we are starting with the third session of the second edition of the Weather and Society Conference. We have had fruitful conversations in the previous two ones, and this one is going to be discussing about dissemination and communication aspects related to early warnings. My name is Isadora Jiménez. I work at Lobelia, an SME based in Barcelona, and I have been working for the last years in the field of climate services and also air quality and shorter term warnings. And I'm a science communication specialist, so most of my questions will be quite related to aspects on language and visual communication. Together with me, there will be Carla, Mooney, and Thomas Cox that will be co-chairing the session and will be in charge in the different blocks of the session. For the good performance of the session, we ask all of you to keep your microphones mute during the session. But we want to have a conversation and discussion. So if you have, after each of the talks, you have questions for the speakers or a general comment you want to give, feel free to say so in the chat, but especially to make the question yourself. So we will be inviting you to switch on your camera if you want, and your mic and make directly the question to the speakers. If you don't feel like doing so, you can post your questions in the chat, and then we will be making the question for you. The first part and the first introduction of the session. And we have an invited talk. So we have here with us Chloe Fletcher, and she works at the Global Health Resilience Group at the Barcelona Supercomputing Center. And this is a team that is led by Dr. Rachel Lowe that co-develops impact-based forecasting models at subseasonal to decadal timescales in collaboration with public health, disaster risk management, and humanitarian agencies. So I could invite Chloe, if you can start sharing your screen, and you have 20 minutes, and later we will have time for questions for Chloe. Thank you.
Okay, brilliant. Can you hear me and see my slides okay?
All okay.
Okay, perfect. So my name is Chloe Fletcher. I'm a PhD candidate in the Global Health Resilience Group at the Barcelona Supercomputing Center, and it's a pleasure to have been invited to speak at the second Weather and Society Conference focused on early warnings for all. So today I'll present a tool we've been developing over the last 6 months called ENDCast. This represents a climate-integrated early warning system for predicting infectious disease outbreaks during El Niño and La Niña events, which is at present tailored to the Latin American and Caribbean region. So I'll briefly introduce what ENDCast is and seeks to address, our methodological framework, and the co-production process to build and implement the early warning system. So to start by reflecting on the relevance of this work, we know that El Niño affects the frequency and intensity of extreme weather events, which can have a detrimental effect on human health. For example, through food insecurity, displacement, and the increased prevalence of vector-borne and waterborne diseases. Now, by the end of the century, an estimated 4.7 billion additional people will be at risk of mosquito-borne diseases, such as dengue and malaria, under the worst-case emission scenario. And this emphasizes the increasing risk of infectious disease burden, morbidity, and mortality under climate change. Now, despite this, there are currently a lack of climate-integrated decision support tools that provide early warnings of outbreaks to inform epidemic preparation, particularly in response to extreme climatic events or seasonal anomalies that are associated with natural phenomena such as El Nino or La Nina. And this really highlights a clear gap in the climate and health arena. So we're currently experiencing an El Nino, which is starting to taper off, and this has very much formed the impetus for our work. Now, the Latin American and Caribbean region was selected as an initial area for the ENDCast prototype due to the high burden of multiple concurrent disease outbreaks, in which 2023 was shown to be a record-breaking year across many countries within this region, particularly for dengue outbreaks. Now, our team at the Global Health Resilience Group have conducted various studies exploring the impact of both El Nino and extreme climatic events on infectious disease risk within this part of the world. And these studies have identified climatic drivers of dengue, malaria, and leptospirosis risk, which can be used to support the development of climate-integrated early warning tools. Now, for the ENDCast project, we wanted to address this lack of tools by developing an early warning framework for infectious disease outbreaks that could explicitly respond to emerging climatic events during El Nino or La Nina. So within our framework, we produce probabilistic forecasts for a range of climate-sensitive diseases across the region, and then we host these forecasts on an operational platform that was co-created with researchers and decision makers in the Latin American and Caribbean region. And these forecasts will be hosted throughout the current El Nino and issued on a monthly basis with a 1 to 6 month outlook. Now, in the future, we look to translate this tool into a framework that could be rapidly and flexibly deployed during any future El Nino or La Nina event in any location or for any climate-sensitive disease. Now, in this study explicitly, we're primarily focusing on 2 mosquito-borne diseases, dengue and malaria, and the waterborne zoonosis leptospirosis, due to evidence of sensitivity to climatic conditions and extreme weather. We're particularly focusing on hotspots which are sensitive to seasonal climatic anomalies during El Nino events, as well as where we already have established collaboration. So obviously El Nino is quite a time-sensitive issue and it's quite a large study. So we really wanted to pick areas where we can have quick facilitation of co-creation and co-development to develop a rapid prototype. And so the 8 hotspots that we have selected are marked on the map on the right-hand side. It might not be super clear, but we're looking at the national level, Barbados, Colombia, Ecuador, and Peru. And then we also include 4 regional area hotspots, including the Brazilian Amazon, the northeast and south of Brazil, and Argentina. And this is because there is known associations with El Nino and temperature and precipitation. So on the left-hand side, we're looking at the KNMI Climate Explorer, which is looking at the correlation between the Nino 3.4 index averaged over December to February and the 3-month average temperatures at a 0 to 5 month lag. So we can see that there is increased temperature, particularly in the western coast and north of South America and in large parts of the Caribbean. And when we look at the same for precipitation, we can see this increased wetness in the northeast of Argentina and southern Brazil and in coastal Latin America, and then some drier conditions marked by blue in the north of South America and in the Caribbean. So in terms of our methodology, how do we actually approach developing this early warning system? I'll briefly go through each step one by one, starting with the data harmonization. So within our framework, we harmonize spatial, epidemiological, and climatic and population data into a single data set made possible with the help of our local partners. And these data are aggregated to an appropriate space-time unit. So to make best use of seasonal climate forecasts, we aggregate our data to the monthly level. In terms of the spatial resolution, this will be highly dependent on discussions with local decision makers and the feasibility of our modeling supercomputing resources. So we selected a range of temperature, precipitation, and Nino indices that were accessible via freely available global climate products to support the reproducibility of the framework in the future, and also for enhancing the interpretability of the outputs. And we've considered a range of lags for these different indices to understand delayed associations between climate and disease risk. Now, the next step is to visualize the data. So this helps us to better understand and explore all the variables and identify potential patterns and anomalies within our data. For example, here's a facet plot showing the time series for, at the top, the disease cases over time per month, the Nino 3.4 index below that, the precipitation, and then lastly, the mean temperature. If we highlight some components within these time series, particularly looking at where the disease cases show an upward peak, we can see that the cases appear to increase with increased Nino and temperature and reduced precipitation. Now, these visualizations don't necessarily inform our final model, but can really help with the later interpretability of the results. And then the third stage is model fitting. So we fit thousands of different combinations of models. So we use a maximum of one of each of our temperature, precipitation, and Nino-based variables. So up to 3 variables in total in each of the different models. And we fit these within a Bayesian modeling framework. So we're interested in seeking the response variables. That's our disease incidence rate. We have up to 3 climate covariates as our variables. And then we also include other sources of variation that could be impacting the disease incidence that are not accounted for by our climate covariates. So we account for seasonal, yearly, and spatial variation as well. And all these are estimated within the Bayesian framework integrated nested Laplace approximation. Then we move on to the model selection. Now we fit these thousands of different models. We need to identify what the best one is. So we compare a range of different model evaluation metrics and exploratory analysis to help us select a small handful of candidate models. These models are we then test some refinements to see if more complex derivations of these can improve their performance. And then we move on to this model verification stage. So this is used to identify the best model for prediction from our small number of refined candidates by evaluating their predictive ability. So to do this, we perform a cross-validation process, removing 1 year out of the time series to see how well the model fills in the missing cases. I won't go into too much detail about that, but I'd be more than happy to discuss that process later. And now we've selected our best model, we need to sense check it and make sure it's interpretable. Now for this, it's essential to discuss results with climate and health researchers in the Latin American and Caribbean region, particularly in each hotspot, as well as with health and meteorological services where possible. And once we're satisfied with this final model, the last step is to produce the monthly forecast. Now, it's important to note that Bayesian modeling incorporates uncertainty by considering a range of possible outcomes, which are expressed as probability distributions. And we do this instead of providing a single deterministic disease prediction in our final output. And this means that we quantify multiple sources of uncertainty to reflect the inherent variability and ambiguity in the underlying data and model parameters. So first source of uncertainty that we take into consideration is in the parameterization of the model itself. So to account for this, we take 1,000 samples from the posterior distribution from each parameter, and this gives us 1,000 possible relationships between our variables and the disease cases. And then our second source of uncertainty is within the data that we use. So in this case, it would be to produce disease forecasts, we need to make use of climate forecasts. So in ENDCast, we use the ECMWF SEAS 5.1 climate forecast with all 51 ensemble members. And when we combine these two sources of uncertainty, we get 51,000 combinations of parameters and covariates to generate our disease predictions. Now we can calculate metrics such as the probability of an outbreak by noting what proportion of these 51,000 predictions exceeds some predefined epidemic threshold. Now, this threshold can be informed by local practice. For example, we may say 300 cases per 100,000 people, or we could do so statistically, such as taking, for example, the 75th percentile of cases historically in that month and location. And it really depends on conversations with local decision makers or what level of risk that they're willing to assume. And then now we have these predictions, they need to be communicated and visualized. So here is an example of a visualization that is typically used by researchers to convey the distribution of predicted disease cases, called a probability density function. The x-axis represents the range of possible outcomes for our predicted cases, with the y-axis representing the density, which is the likelihood of each outcome relative to the other outcomes. And then the solid line here is the epidemic threshold. So whilst it's useful to represent the posterior predictive distribution from a Bayesian model in this way, this type of visualization can be very difficult to translate into public health decision-making. So in this case, the higher area on the right-hand side of this threshold line indicates a high probability of an outbreak. However, this isn't very intuitive just looking at this graphic on its own. A favorable option is to visualize the model-determined outbreak risk level by the spatial unit from each of our forecasts. Now, these outbreak risk levels can be translated from the probability of an outbreak that I mentioned previously, which are derived from all 51,000 predictions. But how do we explicitly determine which outbreak probabilities translate into each risk level, and how are these risk levels established or used? So we've adapted from the risk levels from the WMO, accounting for both likelihood and impact, which was agreed among stakeholders to be easily interpretable scale used for typical climate services. So through conversations with local, national, and regional decision makers, each risk level should translate into a specific action for epidemic preparation, tailored as appropriate to each local context. So there's not necessarily a one-size-fits-all approach here. And these corresponding outbreak probabilities for each category can be informed statistically, so we can explore optimal configuration between getting a true positive rate and a lower false alarm rate, or the decision makers may set the ranges themselves. So for example, we may take an outbreak probability of less than 30% to be low risk, corresponding with routine action. If the outbreak probability is between 30 to 50%, perhaps we say medium risk and to be aware, 50 to 70% high risk, be prepared, and above 70% very high risk and take action. Now, this is just an example, but just to illustrate the point. And in terms of our forecasting scheme, I mentioned that we have a 1 to 6 month outlook, but just to kind of encapsulate that here visually. So if we were to issue a forecast in January, we'd be issuing 6 subsequent target months from February to July. Depending on the optimal prediction model that we've selected, we will make use of a combination of observed and forecasted variables, with a disclaimer that the forecasting skill will reduce as we get further away from our issue month. Now, we recognize that once we issue our monthly forecasts, we need to ensure that the information generated is clear, accessible, timely, and interpretable, and not to forget, actually useful for public health decision making. So therefore, in addition to producing a monthly forecast bulletin, which we're doing at the moment, we will host our forecasts on an operational R-Shiny platform, which has been co-developed with local and regional researchers and decision makers. This includes our partnering research institutes, the Pan American Health Organization, humanitarian agencies such as the Red Cross Red Crescent Climate Center, the Brazil Climate and Health Observatory, and in some partnering countries, we've also been working with National Ministry of Health, Meteorological Services, and Vector Surveillance. So a huge consortium of feedback. So we're looking to have an iterative feedback and two-way knowledge exchange to establish the types of visualizations that can actually aid decision-making. So we did this by holding private meetings, arranging open forums, discussions, and also distributing a survey to gather perspectives on the interpretability and usefulness of each visualization offered within the app. So for each iteration, we've been continuously refining the application to meet these needs. Now, I wanted to give a quick demonstration of the application. So please tell me if you can't see that the screen has changed, but I'm hoping that you can. So this is just,
okay.
Oh, look at, great. So here's a demo of the landing page of our current application. Please note it's a prototype and we still need to work a little bit on the design and kind of styling. But for now, we have this option where you can click on your hotspot on the map, or alternatively, you can navigate to the drop-down menu. And we can access, so what was requested by stakeholders was the ability to access historical data that we're using within the modeling framework. So individuals can explore, for example, here we're looking at the minimum temperature. We can look at this as a time series interactively, so we can see the minimum temperature per month. We can compare these with other variables as well. So we can select another variable and compare how these stack up against each other. Please ignore the legend. That's something we still need to fix. Alternatively, we can look at the annual cycle of different variables as well. We can see what a season might look like, but also isolate individual years. We can explore the annual cycle as a heat map as well, where each element is a month-year combination, and also look at each different variable on a spatial map. So for Barbados, it's not super exciting to look at this map as we're looking at Barbados at the national level. However, for our other case studies, we would see variation in different spatial units across this. So, but again, you can see how this changes over time. We also have a tab for model verification. Unfortunately, I don't really have much time to go through this, but essentially we compare the predictive performance using out-of-sample data for our final prediction model compared to a current practice model. So this kind of confirms the validity of the model. And then lastly, we can move into this forecast tab. I will show you what this risk map looks like in a more interesting case study. But for now, here are some key visualizations that were co-developed, particularly with these local stakeholders. The most sought after graphic is actually this bar chart, which is fairly simple and easily interpretable visualization. So what we're looking at here is, so we're looking at forecasts in the 1900s, obviously not real forecasts, but just for demonstration purposes. So we've issued a forecast in January and we have an outlook from February to July. On the y-axis, we're looking at the probability of an outbreak. Here we can hover over each different bar and it tells us the exact probability. So in this case, 62.8%. And if we use the same ranges that I mentioned previously, this translates into an outbreak risk level of high risk. And we can see that the risk is increasing on a monthly basis and to very high on our third forecasted month with an 86.9% outbreak probability. So this is a way to visualize what probability or what percentage of the 51,000 samples we've generated for each month exceed our epidemic threshold. We can also look at another visualization that was co-developed with these stakeholders, was looking at the range of different values. So the actual outputted predicted values as a dot and whisker plot. So we can look at the mean of these values as the circle, and the range here represents the 95% credible interval of our outputs. And then we also explicitly mark the threshold here. So we can see here it's 13 cases. I forgot to mention previously in the bar chart, we can actually change our threshold level. So this is looking at if our epidemic threshold is the 75th percentile of cases for that particular month. Actually, if we move to wanting to be more sure that there are an outbreak is going to happen, we could move to a 95th percentile, and we can actually see how significantly in this case it affects the probability of an outbreak. So we actually move to a low risk level if we want to be more confident in the outbreak threshold. Lastly, we've also included the probability density function that I mentioned previously. We can look at this month by month using the slider on the left-hand side. We've tried to make this graphic because the feedback we were getting routinely was that it's really useful to have, but it's very difficult to interpret. So our aim was to try and make the graphic as interpretable as possible, which has still been quite a challenge, and we're still working on how we can improve this. But here we have the threshold line, we've marked the shaded area on the right-hand side of the threshold line, which is kind of our area of concern. That's when cases are exceeding this threshold. So this area has been marked in blue, and we actually represent the probability of an outbreak, which is reflecting that area in a table below with the corresponding risk level, and then also marking the threshold here. So that's 13 as well. And then also the prediction mean, which is not intuitive from this graphic. And we can really see how this changes if we set the 95th percentile instead of the 75th percentile, where we move that outbreak threshold from 13 cases to 35.8 cases, and then we can really see that how this outbreak probability drops. So that's just an example of some of the graphics that we include within our framework. And here's another graphic if we were to look at a spatiotemporal case study. So this is the case for Colombia. We can look at the outbreak risk level spatially as a map, and we can use the slider to change our forecast month. So we can see if we hover over an individual spatial unit, we can get the exact risk level as a pop-up box. And if we double click on that spatial unit, then we navigate towards the other graphics for that particular region as well. So I'm just finish up now in terms of how we kind of operate the framework. The first 6 stages of the 7 steps that I mentioned previously will be done ad hoc. So the intention is to create a reproducible pipeline that could be rolled out and applied elsewhere at the start of an El Nino or La Nina event. So there's this process of rapid deployment, and these first 6 steps really help us identify what the final prediction model is. And then this last stage is producing the forecasts that are operated on a monthly basis. So that's the part that actually needs to be operationalized long term. I just want to say a special thank you to our consortium and team across the Latin American and Caribbean region, as well as at the Barcelona Supercomputing Center. This has made the work super possible. And thank you very much for your time.
Thank you very much, Chloe. So now it's time for questions. So Martin and Beth have been commenting. So maybe Beth, if there's any comment you would like to be doing with you directly.
Yeah, no, thank you, Chloe. That was really a beautiful talk, and it looks like a very nice system. And I really appreciate the thought that you're putting into interpretable graphics. And I haven't seen a colored bar chart like that. Probably they exist, but I've found that that would be, you know, it seems like you're getting data across, but you also have that quick look view. So I thought that looked pretty effective.
Brilliant.
Thank you very much.
Yeah, actually the colors in the bar chart were from feedback from stakeholders. We initially just had like blue bars, and they were like, oh, it would actually be really easy to have that, exactly that very quick perception of the risk just by quick inspection.
Perfect. Martin? I think I also had that question, so go ahead and ask it.
Yeah, so thanks a lot for this very nice presentation and this work. So you said that the predicted PDF was said to be too difficult to understand. Do you have more information about what they meant by too difficult? Do you test that somehow, or?
I think it was more from the perspective of the decision makers. So if they wanted to quickly make a decision, or if they wanted to evaluate the risk, just looking at the graphic on its own, it was quite difficult to interpret, you know, what proportion of the samples have exceeded the threshold. I think the feedback was thinking in aerial terms, because essentially you're looking at the probability of an outbreak represented as an area, which I think can be quite challenging when comparing. I mean, some of our outputs, the PDF looks a bit different to that one. And sometimes it can be quite challenging to get that exact kind of, right, what level of risk are we talking about? What do we do with this? So I think the feedback was, you know, if we provide additional statistics at the bottom of the graphic, it would be more interpretable. So we can see exactly what those figures are, how they translate into the risk level. And then also, I think coloring it slightly differently helps them focus on the area of, you know, the bit that's actually concerning. Perhaps we need to work on the color palette a little bit more, but that so far has been keeping it, because we want to be able to represent the distribution. We don't want to remove it. So we've been really working to see how we can retain it. So yeah.
So it's more about the statistical presentation than the fact that it's kind of an impact forecast and not a meteorological one. Okay.
So yeah, one of the things related to this question, I'm sorry, I realized now it was David Hoffman making the question, but so you were saying that you were co-producing the service with this public health decision makers. I understand that they are technical people who understand, but have you seen a leap between what you were producing, what they could understand, and which is the next step? So do they provide this information as it is, or they do a second level of simplification of the information within their institutions before making decisions on how to address an outbreak?
Yeah, that's something we're still figuring out at the moment. So we've developed this prototype application with the idea that, you know, for this current El Nino, this application will work in the interim. We're discussing further funding opportunities, perhaps at the regional level, to increase and improve the application itself to make sure it's sustainable. This is a really key challenge, and make sure it's scalable. So like right now, there will be a direct interaction with the application. Local decision makers will have private access to their particular hotspot, as there's currently data privacy concerns, which we will need to address. But in the future, yeah, how this translates necessarily into public health decision making, there's still a gap there that we need to bridge. So in the next few months, we'll be having more direct conversations with hopefully the Ministry of Health and Meteorological Services in each country. And at the regional level, how we may kind of scale this up a little bit more as well. So this is definitely a space. There's still room for more discussion and improvement there.
Perfect. Yeah, I really think it's this part of how you translate these probabilities into thresholds is really important part of the conversation that I'm sure we're going to be finding in the following task. Thank you very much, Chloe. For all the attendees, she will be later in Gathertown. So if you want to approach her and have a bit more of a discussion with her regarding this early warning and all this process of visualizing and providing the information, she will be available. So now we jump into the first block of talks. We have 4 invited talks. And the first, before I go into it, I forgot at the start to let you know that besides specific questions that you can have for the session, comments, feel free, if not a question, but something that you want to contribute with your experience and in similar topics, feel free to let us know. But there's a Slido link that we will be sharing in the chat, which is more about this specific type of questions that are arising related to communication and dissemination that you think that it could be interested to be discussing further, because all this is going to support the discussion that we will have in the collaborative session that we will have in a few weeks after the conference. So feel free to add these more general questions that as a community we need to tackle. I jump now into the first talk. Unfortunately, because of the time zone, our speaker, so Majumdar from University of Miami in USA, cannot be in person, but has shared the presentation, so I will be sharing now.
Thank you for the opportunity to present at this online conference. Apologies that I couldn't do this live, as it's in the middle of the night my time. The title of this project is Dynamic Communication of Weather Risk, a user-centered design approach, and it represents a collaboration between the University of Miami and NCAR, and also a collaboration with our stakeholders at NOAA. And we gratefully acknowledge funding from the NOAA Social Science. So this project germinated in 2018 when a team of 5 faculty from different disciplines came together under some seed funding from our university with this specific goal to contribute to the design of an information provision system that communicates the minimal critical pieces of information to the maximum number of people from diverse backgrounds. And the first step in our approach was to do some public evaluations of the US National Hurricane Center's cone of uncertainty. So here's a list of our activities. In particular, we completed a literature review for BAMS, and we conducted some public focus groups in the lower right-hand corner here, and also a public online survey. We performed some visualization experiments for the cone of uncertainty and also some experimental redesigns, as we see in the top right-hand corner. And then we also engaged students, stakeholders, and the public in several different ways, as well as interviewing TV meteorologists. So we've used a mixed methods approach ever since we began the project, even when we were working on the cone. Some lessons learned from this first project is that it's a very interdisciplinary problem. Even for something as specific as the cone and a hurricane. So the cone is generally the most widely used forecast product, but there are systematic misinterpretations. That's not only related to the cone itself, but to the surrounding elements. And we found that modifications to the cone that were based on user experience lab experiments yielded similar results. And we found that these results varied from storm to storm, more so than based on the different modifications. In our public survey and the focus groups, we found that most people generally consulted and trusted TV more so than the other sources. Also, an important point is that social vulnerabilities that contribute to the risk are not always considered in the forecast product. So we wanted to try and address that and develop products that are more focused on people's needs. So the direction that we've headed in since 2021 is to think about risk and impact-based graphical displays that better communicate the types of hazards that one might be anticipating, and less focus on the path of the storm, especially during the timelines of evacuations and other decisions that need to be made. For further information, you can check our papers that are listed here. On to the current project. So we're using the US National Weather Service Hurricane Threats and Impacts graphics as a starting point. And so their operational graphics have 4 different types of threat: wind, storm surge, flooding rain, and tornado, with different color scales to show the different potential levels of severity, for example, high storm surge or high flooding rain threat. This is for Hurricane Irma that was a threat to much of the state of Florida in 2017. So the goal of our project is to advance the effective visual communication of forecast risk and uncertainty by including probabilistic information and hazard threat levels. And so we use a 2-step approach. That the first is to use public feedback in the design of new visualizations, and then the next step is to evaluate the visualizations. And so those are the foci of the rest of this talk. Our project flow is that we develop generative research through our own discussions with NOAA and also with design charrettes that we'll discuss in just a couple of minutes. And we use this to design new visualizations, and then we evaluate these prototypes through public online experiments, as well as with broadcast meteorologists in the private sector and emergency managers. Then an end goal and a key deliverable to NOAA would be the provision of design guidelines based on all of these experiences and feedback. So we began with 4 design charrettes in the city of Miami. We used 4 different community organizations, and here are some of their missions that are listed above here. And here are a couple of pictures of the design charrettes in action here, that these took place in 2022. And we gave the participants these modified hurricane threats and impacts graphics here that were designed by our expert graphical designer, Alberto Cairo. And we asked the participants to respond to these, at what they liked, what they didn't like, what they found confusing. An example was this tornado graphic where there's just this sea of yellow across the whole state that people are asking, well, what does that mean to them? That is everybody at risk, and how does one respond? And based on the critiques by the participants, that we asked them to draw what they would like to see that perhaps makes that uses a graphic to help them make a decision about what to do and when to do it. And so their sketches and their verbal feedback then led to us redesigning some of these HTI graphics with a whole set of different updates. And here are just a few of them here. One is the color scheme. Another is putting some more specific geographic references, such as the major cities in the state of Florida here. Some text that explains what some of the different risks mean in each of the different categories. We decided to de-identify the storms so that the public did not associate it with a historic hurricane. We used some modern aesthetics, and also we decided to exclude the tornado graphic since the response that we had to the HTI tornado graphics was largely that people didn't really know what to do with it. But stay tuned for feedback on that too. Okay, then on to the evaluations. We have at the University of Miami, led by Barbara Millet, 3 exploratory studies. And so the goals there are to explore the impact of the following attributes to inform the visualization design of a new graphical weather risk product. So the first attribute is the likelihood levels and labels, and that's what we'll talk about over the next few slides. Then work in progress is doing some public tests of graphics that explain the arrival times. And then the third is the presentation of information on combined threats. And so that could be done through text, or it could be done through a series of icons representing the respective threats. And so that one is imminent to begin. And then these will culminate in a main experiment in which the impact of the weather risk visualization design will be evaluated on public comprehension, risk perception, behavioral intent, and user preference. And also, in conjunction with these studies, we also conducted, through our partners at ENDCast, interviews with broadcast meteorologists and emergency managers, and we'll mention a couple of key findings from those in just a couple of minutes. We'll first move to exploratory study 1, and so this was about testing the risk categories and labels. So these were done remotely through Qualtrics and asynchronously. Our independent variables were the design, and we'll explain these on the next few slides. Then we separated the sample into coastal communities that are more prone to hurricanes and inland communities that are prone to perhaps some of the hazards such as flooding, but not storm surge. And we used 3 different tropical cyclones. So these are their real names. They were historic storms, but then we gave them fictitious names so that there wasn't any association with these storms. We randomly assigned one design to the participants and then randomly presented all tropical cyclones for each design. So here's one of the designs. This is with 3 different labels, high, moderate, and the lowest one being slight here, for 3 different hazards. We notice we call the second one coastal flooding. We're going to change that to storm surge based on feedback from NOAA and from the broadcast managers, broadcast meteorologists and emergency managers. Okay, that was our first exploratory study design. The next one was quite similar, except we used moderate for the lowest threat level. We're also showing here some of the geographical regions for the participants. We see there are a couple of counties here that are in hurricane-prone areas, and so we targeted participants in this area, so they were part of that coastal subset of participants. Then the third design was with 4 labels here: extreme, high, moderate, and slight. And also we're showing an example of an inland county in Florida where they may receive more of the rain threat and less of the storm surge threat, for example. 368 participants took part. This experiment was carefully designed that there are equal samples for each design and also equal samples for inland residents versus coastal residents. And we also made sure to have respondents be representative of the gender, age, racial, and ethnic distributions of the United States population. And then our measures here are the perception of risk, whether they would take protective actions, and their preferences of the number of risk categories and what the label was on those categories for the lowest and the highest risks. The key findings were, for the risk perception, that it was influenced by both the number of risk categories and the risk labels. This needs further exploration. For the preparatory actions, the decisions are based on the storm characteristics more so than our carefully done designs. The risk category labels, the participants preferred low for the lowest risk category, but then they also designed more granularity, that 4 was better than 3 for the number of levels. So that's what we'll use in our forthcoming experiments. Onto the broadcast meteorologists and emergency managers, that the goal was to elicit the perspectives on these initial prototype graphics, including how they may use them and also feedback on areas for improvement. So this was very much a two-way conversation. The sample it focused on professionals who are in hurricane-prone regions at several different levels, and we overall interviewed 20 people in total with a range of experiences and working across a range of different markets. The interviews were online and they were semi-structured, and the analysis has been done. That's an initial thematic analysis focused on a prototype redesign. So key findings: the participants like the prototype and how it improves upon the current graphics, and there was general approval of the 4-color scheme and the updated colors. They did want to see the tornado hazard in there as well. That's something that they'd like to present to their stakeholders, that is the public. They made several other comments that I won't read out here, but those really informed us on the next series of graphics to design. And there's an important point here, that not one graphic can accomplish all the communication goals, that there's a diverse set of needs and uses by professionals and also by the public. So the next steps in this part of the study is the integration of the findings with results from the exploratory studies, and that will help with the final experiment and the design guidelines, and also a further analysis of the interview data. So we'll just wrap up here that we've mentioned ES1 and the interviews, and so we have ES2 and ES3 left, and then also the main experiment, which is planned for this summer. And then the ultimate goal is to synthesize all of these into a comprehensive set of design guidelines for NOAA. So I'll stop there and thank everybody for your attention. Feel free to contact me at any time. Thank you. Bye-bye.
So unfortunately, we cannot make questions, but as he was saying, we can be sharing any question with him. So feel free to write to the email of the conference. Before going directly to the next talk, I just would like to highlight one thing that stood out from this presentation, and it's linked to Chloe's presentation, is the importance of the use of colors. I will take all opportunities I have to speak loud about the importance of the color schemes used, and particularly to always and not to forget colorblind friendly palettes. And you see for the hurricane that even having 3-4 levels, they have avoided green, orange, and red, while going for a gradient of reds or different color schemes. And I think this is something that we all taking on the visualization of communication products to be taking this into account. Nico, if you can start sharing your screen.
Yes, I will do that. Okay, thanks for giving me the opportunity to give this presentation here. I will talk about some latest results which we have from experiments where we looked at the effects of weather-related road accident forecasts on risk perception and on travel decisions, which we have done with colleagues from Max Planck Institute for Human Development within the framework of the Hans Ertl Center for Weather Research. But first, let me introduce you to Sophie. Sophie is living in Berlin and she's 25 years old and just finished her university degree, and now she's desperately searching for a new job. And she's written many applications, and now she's got a job interview tomorrow at 11 in Hamburg. And Hamburg is a 3-hour car ride from Berlin. And she knows she has to get there. And now she gets the weather forecast, which tells her that there will be snow tomorrow. And of course, she knows snow may lead to accidents somehow, but this is more like a qualitative knowledge. She doesn't know how likely it is actually that there will be accidents. So she asks herself, will there be any accidents? Should I leave earlier because there might be delays, or should I even take the train because that's more safe than riding the car? So she asks herself, would forecasts of accident probabilities somehow affect my decisions? And we thought, oh, we can study that. We just need to develop a model to forecast accident probabilities and then conduct an online experiment to test how these forecasts affect the users. So the first thing we did was developing an accident model. And for that, we took 6 years of accident records for Germany. Then we took radar-based hourly precipitation sums on a high spatial resolution, and we took temperatures from regional reanalysis data, and we combined all that in a logistic regression model. And we used this model to predict the probability to have at least one accident caused by road conditions in 1 hour in a certain district. So we can make predictions for all districts in Germany. And this is just a snapshot of how this model looks like. You have the precipitation on the x-axis and the accident probability on the y-axis. And you see that with increasing precipitation, the accident probability increases. And at negative temperatures, the accident probability in case of precipitation is about 5 times higher than under positive temperatures. So now we implemented this model in a real-time forecasting system, and then we wanted to see how users react to this kind of forecast. So we made an experimental design, which I will introduce shortly. So we introduced like the scenario of Sophie to all the participants, like they had a job interview the next day and they had to take a 3-hour car ride. We randomly allocated all of the participants into 3 groups, and these 3 groups received different forecast information. Group 1 is the control group, which only receives weather information, and then we have 2 groups which additionally receive different types of accident probabilities. Each of the participants is shown in a random order 9 different weather conditions, and for each weather condition we asked them questions on risk perception and travel behavior, and after that we asked them about other things like how useful they find these forecasts, and of course we collect some demographic variables about age and education and so on. We had a sample of 772 participants, which we collected via quota sampling, and we paid them for their participation. So on the next slide, I will show you in more detail how these 3 different experimental groups looked like. The control group, which only received weather information, got a map with precipitation forecasts and temperature forecasts, and they see like the route they have to travel on the next morning. The group number 2 additionally received accident probability forecasts, which we predicted using our accident model. So they see for each district how large is the predicted accident probability. For example, here in these districts with high probabilities, the probability exceeds something like 20%. This is what we call the absolute accident probability, and the group 3 receives something which we call the relative accident probability, which is the probability to have an accident compared to warm and dry conditions. For example, it tells them that in this area, the accident probability under these conditions is about 100 times higher than under warm and dry conditions. So these are the three groups, and to all of the participants, I already mentioned that we show them different weather conditions. In total, they get 9 different weather conditions, which can be categorized roughly in these 4 categories. So we have one situation with light rain, 3 situations with heavy rain, then some light snow situations, and some heavy snow situations. So for all of these situations, we asked the participants questions about risk perception. So the first question we asked is, how high do you estimate the probability that there will be a traffic accident on your route due to the weather conditions? And then we went ahead and built linear mixed effect models to describe how the different types of participants answered this question. And now we can come back to Sophie and plug all the information about Sophie into this model. For example, we say age is 25, female, gender, university degree, and now we can select the group. So if Sophie was in group 1, which received only the weather information, and we show them the light rain condition, she would have estimated an accident probability on the whole route of 15.7%. So this number alone is not really interesting. It gets interesting when we look how this estimated probability changes if we show her different forecast information. So this is how she would have reacted if she was in group 2, which got the absolute accident probability. And you see that she would have estimated a lower probability for the whole route. So the risk perception is lower if she gets these absolute accident probabilities. If she also gets the relative accident probability, this effect is kind of removed. Then you see the error bars are quite large here, so there's no really significant effect of this accident information on her risk perception. If you look how the different weather conditions affect this risk perception, you see that the different kinds of weather conditions have different effect. The largest effect is the heavy snowfall, which is kind of expected that if you see this is a really dangerous situation, you estimate a high accident probability. We also asked them about their intended behavior. One question was, for example, if they would leave earlier due to traffic delays or so, and how many minutes they would leave earlier. And we have the same procedure. We build a model and we plug in the information about Sophie, and we see that under these light rain conditions, if she would only receive the weather information, she would leave 8.8 minutes earlier. If we look at again at the effect that the different forecast information have, we again see a similar picture that if we provide her also the absolute accident probabilities, this number would reduce. So she would not leave earlier, but she would only leave, if you compute this, something like she would only leave 3 minutes earlier. And again, if she gets the relative accident probabilities, this effect disappears again. So this kind of balances the effect of the absolute probabilities. Again, you see that if, for example, in the high snowfall situations, she would even leave like about 25 minutes earlier than in the light conditions. Another question we ask is, how likely do you think it is that you would take the train instead of the car? Same thing as before. The likelihood that she would take the train is 15.8%. And here, if you look at the effect of the accident forecasts, you see again there's a large uncertainty, so a large variability within the group. So you can conclude that there's no real effect of these different forecast product on this decision about taking the train. So there might be other factors that are much more important. For example, how often they use the train in general compared to using the car. And again, the weather situation plays an important role. So in the more dangerous situations, they are much more likely to take the train compared to the light rain situations. What we also asked them were questions about how useful they find these accident forecast products. And we asked them if they would download these forecasts if it was available as an app. And about 70% of the participants said that they would download that, and many of them would even pay for such an app. We also asked, how useful do you find these forecasts for planning your travel? And we differentiated between the different forecasts.
You have 1 more minute.
Okay,
One more minute to go.
Thanks. Between the different forecast products like temperature, precipitation, and the 2 accident probabilities. And you see that about 50% of the people find these kind of forecasts to some extent useful, which is quite a nice result. So I quickly summarize what I've told you. And I have like 3 take-home messages here. First one is that if you're communicating these absolute accident probabilities, this lowers the risk perception and the likelihood to change the behavior. But if you communicate additionally relative accident probabilities, this kind of compensates this effect. And also, although the effects of this accident forecast on risk perception and decision making is not that large compared to the effect of the weather situations, users tend to find such forecasts understandable and useful. And kind of Sophie would summarize this something like that accident forecasts might be useful to the users, but the format in which they are communicated needs to be carefully tested in how the effect actually looks like. And with that, I end here, and I'm happy to answer any questions.
Thank you very much. So first there's a hand up, Marcel.
Yeah, can you hear me?
Yes.
Yes.
Perfect. Thank you very much, Nico, for your nice presentation. When you were showing the products, the warning products to the people that were doing the tests, I noticed that you used quite neutral colors, so no signal colors. Was this intentionally? And if not, do you think that the outcome would change if we're using different colors?
Yeah, I mean, we used this intentionally, also for the reasons that Isadora mentioned before, that we made sure that this was kind of colorblind friendly. And I think that it might definitely have an effect on how you choose these colors. Yeah, it might be that if you choose more intensive colors for the accident probabilities, that this might have a different effect on the reactions. Yeah.
Thank you.
Now there is a question by David Hoffman, if you can jump in.
Yeah, thank you. I just leave my camera off because I got a notification that my internet connection is a bit wonky. Thank you for the talk, Nico. It was very interesting. I noticed on the plots that you showed with the different forecasts and accident probabilities that not just the route between Hamburg and Berlin was shown, but also between other cities. And I was wondering if they were all put in one pot or if you found differences in the localities of the routes. For example, I know that Bavaria is more prone to heavy snowfall than northern states, and even under the same forecast and accident probabilities, if there were any differences in the outcome.
So we used 3 different roads, one in the north, one in the center, and one in the south of Germany. But we made sure that kind of each of these routes was somehow affected by different weather situations. We have not looked really at the systematically if these different routes have different effects, but kind of we try to control that by assigning this weather situation category to each situation.
Perfect. And Adrian Perez, if you want to ask your question directly. And
yeah.
If not, yeah, perfect.
Hello. Good day. Thank you for your presentation. I've been doing such a study a few years ago and also went through a lot of literature. There's quite some literature on this. And my main question is, or one of my main questions is how you define accident probability. I would expect from the point of view of a driver that you're assessing that in to what extent it differs from the default accident probability there is anyhow on the roads. In most countries, 80 to 90% of the accidents has no or a very weak relation with weather, in fact. So weather is increasing it, and of course, at very specific moments, weather can of course be very important. So I wonder how you, for example, have been looking to that, partly also because weather can already take away the whole reason to take the trip, to make the trip in the first place, for example. So my main thing is indeed how you define probability, because I was a little bit amazed by it. Perhaps I misunderstood it.
Yeah, maybe I went a bit quickly over that. So the accidents that we looked at were only accidents which were assigned by the police to be caused by the road condition, which includes mainly wet road or icy road or snow on the road. So so we from our model we excluded all accidents which were likely not caused by the weather conditions. So that's why you see in the model this strong effect of the weather. So if you would take all accidents in general, of course there are much more accidents which are not caused by weather, but these accidents which we included made up about 7% of all accidents in the database, which were kind of assigned to this accident cause, which is called road condition.
Perfect. Thank you very much. There's another question in the chat, but for the sake of time, I please ask you to follow on with the conversations with Nico Becker later in Gathertown, as long as he can be with us. So I ask please Jouke de Baar, our next talk, to be sharing your screen and going ahead. We're a bit below the time, but I really look forward for these conversations and yeah. So Jouke, if you can be sharing your screen.
So yeah, good morning and good afternoon and good evening, I guess, to everyone around the world. And this is a question that I discuss at home quite often with our daughter. So when cycling, the chances of falling are pretty small. So why would we wear a helmet? And of course, we all know the reason, that if you fall, the impact can be quite high. And this is an example that makes it easy for us also to talk with stakeholders in impact forecasting, and I'll try to explain a little bit. So this presentation is about what happens after we make an impact forecast, and we think there can be a really nice way in collaborative decision support with stakeholders, and we focus on storm impact, and this is actually a joint presentation between the safety region. So I'll explain what the safety region is, and our Netherlands Met Service, the KNMI. So in the Netherlands we have 25 safety regions, and they were established in the Safety Regions Act in 2010. So on the right you see a map of the Netherlands with all our safety regions, and in this study we focus on two safety regions, which are called Brabant Noord and Brabant Zuidoost. And we've been collaborating with people from those two safety regions. And in that safety region, they have combined in a single dispatch center in the north. So why do we have safety regions? They were started to have a more effective cooperation between fire brigade, police, and ambulance services. And it was started after two big disasters that we had. So we had actually an explosion of a fireworks factory in 2000. And then in 2001, on New Year's Eve, we had a huge fire in a pub in the city of Volendam. And as a result of those accidents, we have set up the safety regions, and it's a place where the emergency services work together, and they deal with crises and disasters and other disruptions, and they work closely with the municipalities, who are also an essential element of this safety chain. So the most important task of the safety region is to prevent and limit fires and accidents. So that's what the fire brigade does. And that can also involve the consequences of extreme weather. So what we try to do in this project is, it's a pilot project, and we try to make impact forecasts for storm damage, but also to support the dialogue between the safety region and the Met Service. And we really try to combine the expertise from those two domains. So the first part is to make an impact forecast, and we collected 10 years of emergency calls to the dispatch center of the safety region. So when people observe storm damage, they can call the national alarm number, and they can call for help, and the dispatch center will respond to the emergency. And on the left, you see the observed number of emergency calls to the dispatch center on a 10 by 10 kilometer grid in this region. So each dot is a 10 by 10 kilometer grid cell, and the color indicates the number of calls that were received from that area, and that the dispatch center had to respond to. So this is during Storm Eunice. So this is the actually observed number of calls, and this is a forecast with a very simple model for the same 24 hours. And we do have a more complicated way of making a forecast on a higher resolution based on the numerical weather product. But the forecast that we use here is actually a simpler, more simple forecast, and it's also just based on observed wind speed. So in that sense, it's not really a forecast, but it's a tool to discuss and work with the safety region. And at the top, you see the expected number of emergency calls, and at the bottom right, you see the same picture, but then the expected number of calls is represented as an ensemble. So the top right and bottom right are the same forecast, but on the top you see the expected number, and at the bottom you see the ensemble forecast. But we really try to forecast the number of calls that they will receive. And then how do we interact with the safety region? So we can make an effect matrix with them. So this is a very simple model. So if nothing goes wrong and they don't take some preventative action that they might be thinking of, then the added effect is 0. If they do take some preventative action but nothing goes wrong, then there might be some cost, so some effect. So in the case of wearing a bicycle helmet, you might have a warm head and it might be a bit uncomfortable. But then if you have taken action and it does go wrong, then the effect is still limited. And of course, if you don't take action and it does go wrong, the effect can be much larger. And actually this we can compute, we can multiply with the chances, and then we get an expected effect, and we can add the expected effect, and then you can see that in the long run, in this example, it might be wiser to actually take action, even if the chances of something going wrong are pretty small. So this is a really simple example where we try to combine the knowledge domain of the safety region with the Met Service knowledge domain. So they provide the effect matrix and we provide the probabilities. And we can do this in an interactive way in a graphical user interface with them. And then if you think about it, it's related to this data value chain that we think of. So we collect data, we process it into information, and then later on in the chain, a decision is made and action is taken, and hopefully it leads to value for society. And in the classical way, these roles of the Met Service and the safety region are quite separated. And what we're exploring in this pilot is to create more overlap in that chain. So as an example, we spent a shift at the dispatch center in Den Bosch to see how they really operate and how the fire services respond to emergency calls. So we worked out 2 case studies. The first case study is if a storm is coming, should the dispatch center take precautionary action by having an additional dispatcher, so an additional person in the center. So this is a hypothetical decision that we worked out together with the dispatch center. So they assume that normally they can handle like 30 of these storm emergency calls a day. And well, what happens if there are more? And a decision that they might take is that they have as a precaution an additional person as dispatcher for 24 hours in the dispatch center. And we filled in an hypothetical effect matrix. And of course, it should be clear that filling in this effect matrix is really the knowledge domain of the dispatch center in this case. But what you can then do is go through 10 years of storms. So on the horizontal axis, you see the time in years. And then on the vertical axis, you see the cumulative added effect on society. And the gray area is the decision space. So the lower limit of the gray area is like, if in hindsight you would know the number of emergency calls and you would have always taken the right decision in adding a person or not adding a person. And the upper limit is if you, in hindsight, would always be able to make the wrong decision, so the worst possible case. And then the dotted line indicates the normal situation where you never add an additional person in the dispatch center. And the continuous line is if you always add additional dispatcher. And then if you start using the impact forecast, we arrive at the blue line. So that is if they use this interactive tool and they start making decisions based on the impact forecast. And the blue line is actually if we communicate a single impact forecast, so the most likely number of calls. And the red line is what happens if we communicate an ensemble of impact forecasts. And of course, there is a difference because in the ensemble, there might still be cases that are above their capacity and they would still take the safe decision, like when wearing a bicycle.
One more minute.
Yeah. And then we did the same exercise, but now we filled in the effect matrix for the individual fire stations. So they have about 50 volunteer fire stations in that area. And normally these volunteers are called from home if there's an incident, but they could also send them to the fire station in advance for a shift. And of course, we can fill in the effect matrix, and then you'd see this kind of cumulative added effect on society. So again, you see actually the best decisions are made when we communicate an impact ensemble. So thank you very much for your attention, and yeah, I would be happy to take questions, and also at the bottom is my email address.
Thank you very much, Jouke. Is there any question by the audience? So we see some reactions. So if there's no other question, I just would like to maybe clarify, maybe you have said at the beginning, how is the tool, the forecast on itself, expected to be shared? Is this something that is going to be provided online? Is this a report that is handed to the safety region? And particularly if the people in the safety region collaborating with you are the ones that are going to be making decisions out of these forecasts?
Yeah, so they are the decision maker, and we have a prototype tool. It actually looks like this. So this is for the same example. And this is this is how they can interact with our forecast. So what you see here is that they select the area that they're responsible for example, the municipality or the number of fire stations that they're interested in. And so, yeah, we really think that this is a way of having an interactive tool that can help them make the decision. And so they fill out the effect matrix, and then the tool computes the expected effect of not taking an action or of taking action. So this is how we are now thinking of providing the information. Yeah.
Perfect. Thank you very much. If later any of you has additional questions, you can follow on the chat or in Gather Town a bit later. So we move forward for Anders Sivle.
Yeah, I think you can see it now.
Yes.
Okay, thank you for the opportunity to talk about language today. I will report from a Norwegian project. You can see a lot of participants in this project and several organizations where we worked with plain language and how we can use that to structure the warning communication and also to raise situational awareness. To switch your minds a little bit from graphics and colors to language, this is a very brief look at warning communication. And I think that the main aim with the communication is that we want people to act, or at least we want them to consider to act. And much of that is based on the recommendations from WMO a few years back, where they said that it's not enough to forecast just the weather. You have to give information about the impacts also to make it easier for people to know how to act. And when I briefly looked around the world, how we do it, focusing on language, it looks like this in the UK, the US, and Australia. You can see that it's pretty much like WMO recommends. You can find information about the weather situation, how it's going to be, and also indications of impacts of the weather and some behavioral advices presented slightly differently. If we look at the warnings in Norway, they look almost the same, you could say. You can find the headings with description, consequences, and recommendations what to do. These headings are taken more or less straight from the CAP format, and it makes the warning easy to scan, but perhaps also a little bit difficult to see the key message. You have to read quite a lot, and for each of these consequences and recommendations, you have to scan through and read through maybe 6, 7 bullet points. You can also, there will also be a bit repetition between the points. So in this project, we had a service design approach, and we wanted to dig deeper into the thoughts of people and how they think about language used in the forecasts. So the starting point was reviewing literature and studies that already existed. Quite a lot of work is done, not only on language, but on warning communication. And as we have been listening earlier today, colors are frequently used in warning communications, and they are also quite intuitive. It's similar to the traffic lights. Red is more severe than yellow, but even if you know that red is dangerous, it's not intuitive what you should do when you see a red color. So behavioral advices, as suggested by WMO, help people to understand the consequences of the weather and to know what to do. But still, for example, people that are new to a country because they are tourists or immigrants or just moving around, find it a bit more difficult because the society works differently, the infrastructure is different, and maybe they move from one climate region to another. And for example, a yellow wind warning might not be the same in Japan and the US and Norway. It's slightly different, it's not standardized. Language can also be an obstacle sometimes if you don't know the jargon used, or if the language in the warning is not your first language, for example. The result is the same, independent of these. It can be difficult to know what to do. So we decided to do some fieldwork in a local community in Norway and meet with as many different actors as we could in this community. So we had a workshop with preparedness actors, for example, the police, fire department, people working with power lines from the health, and so on. And we asked them about their timeline when a warning was issued, what the information needs they had was, and how they communicated together. And one thing that stood out after this workshop was that they said that they have control, or quite good control, of the consequences of the weather for their own department, but there is a lack of or a need for a common situational awareness for the community as a whole across the different actors, and I found that challenging. At the same time, we had a meeting in the library in this municipality, and we did some in-depth interviews with inhabitants, and we also asked people that came to the library to build their own warning, and they could select 4 different elements that are typically found in a warning, and they had to put it in the preferred sequence. So what we see based on this small exercise is that the description of the weather and the impacts are very important for the people that were asked to build a warning, but the sequence was a bit varying, what they preferred on top of the warning. But still, when analyzing all insights, it seems that it's important to understand the situation, and you need the description of the weather situation before you can start assessing what to do and to plan your actions. And that should be reflected in the structure of the warning. We also did a text analysis of warning information found on different Norwegian platforms and channels, and they look, as you can see, it's a variation in how they look, the design and the structure, even if it's based on more or less the same warning content. So it's presented differently. And this variation is found confusing by some users because they think it's different information, but it's just a presentation that's different. So the hypothesis is that a more similar design and structure can improve and help understanding the content. So how can we use plain language in the warning communication? With plain language, we mean that the people reading it should find the information that they need. They should understand what they find and be able to use that information in their decisions. So our suggestion is like this. It's not yet implemented, but this is the idea that we work with, that the description of the hazard should be presented early on, first in the message. And for specialist users, this is often enough information because if they know how much rain it's going to be, when and where, it's often enough for them to know the local consequences. And after this, we suggest to put together the consequences and the instructions to avoid repetition and to place them under new headings. And the headings are more thematic and describe in clear what is going to happen, the main consequences. So rather than listing 6, 7, 8 different consequences, we put it all together to some main consequences. And just by scanning the headings, very heavy rain, difficult driving conditions, and risk of water damage, you should get the main message of the warning. And you can choose to go deeper if you want and read more. What we see when we go through all the different weather types is that very often one of the headings is about transport and one other heading is about having property or securing lives. You can also add more elements like the timeline and graphics in addition, but the focus now is on the language. We did ask people how what they think about the new structure. The feedback is that it's easier to read, it's easy to scan and see the key message. The sequence of the information is logic, and it gives a quick situational awareness. The preparedness actors that we talked to agree and say that this can actually be helpful for a common understanding of the situation for them as well. And the forecasters we've talked to also like it so far and think that they might have more control of the outcome of the communication doing it this way. We also think that the headings can be reused in other situations. For example, they can be easily integrated into notifications and mobile applications, or they can be used to ease communication with media because we have a few points about what is happening that is easy to communicate. So to sum it up, we think that a new structure using plain language with thematic headings makes sense for inhabitants, for preparedness actors, and forecasters. They're easy to scan, they provide a key message and a common understanding of the situation. So now the project is over, but we are still working to try to implement this in our weather services. Thank you.
Thank you very much, Anders. And I look forward for some questions by the audience. Okay, so Natalie, if you're happy to jump in, for her it's not clear whether this new design is compatible with the CAP standard, CAP.
Yes, we have discussed that with the people working with the CAP profile in Norway, and to say that it's quite easy because the CAP standard is flexible as well. But that means that you have to make a local parameter in the CAP where you put the new headings and the new content elements. Because we know that some global actors use the standard parameters, you should provide both the standard parameters as you do today, and the new ones that can be used locally to make it easy for everyone to find it. But it's possible.
I myself, I have a broader question, which is, this is really interesting. When we saw the talk title, we really wanted to bring language, not only the language, if it's English, the local language, but also how we put text into all these warnings. So it's really interesting. I would like to know how all these learnings from this project are expected to be shared with the broader early warning community, other Met services, and what are you doing to disseminate these learnings?
Attending conferences. We would like to, at the moment, it's just a report in Norwegian, so it's not so easy for others, but we are planning to write a report or a publication that is easier to share. So, but it will take some time to do it.
I take the opportunity to let you all participants in the session that the World Weather Research Programme is setting up now a core research project that is going to be called People, where all these aspects of social sciences from either communication but also behavioral response are going to be taken into account. So all these learnings are part of the type of things that could be interacting with this project, to use the platform of the World Weather Research Programme to disseminate further, not only in Europe, but worldwide about all this. You will learn more about this in the closing talk on Friday, and also in the workshop that will be carried out. So we would really like to have your inputs and ideas on how we take this type of research into account and promote it further. Let me see if there's a specific question. One more. We have time for one more. I'm not sure.
I see that there are several questions, so I can answer them in the chat afterward. Yeah.
So thank you, everyone. We're going to make a short break of 15 minutes. And then after these 15 minutes, we will come back, and Thomas Cox will be chairing the session for the next talks.
So thank you, everyone, for coming back to our session. My name is Thomas Cox. I'm from the Weizenbaum-Institute in Berlin, Germany. We work on the digitalization of society, everything what's related to digitalization and networked society and IoT, stuff like this. And we're especially interested in the communication of warnings. So that was really, really nice to hear this talks earlier on. And I'm really looking forward to our next part of the session. We have 4 interesting talks. One will be presented via video, but the others are here. Before we start, a quick reminder: if you have any questions to the talks, please raise your hand and we can pick you up so you can speak. You can use your video if you want, but you can also only use a microphone. If you don't want to use both, please feel free to use the chat. I will either read it out loud, or maybe the presenters can answer the questions directly in the chat. And there's also always the opportunity to come together town later on, so we can discuss things in person, directly face to face, or in smaller groups. So we have 12 minutes talks now with roughly 3 minutes Q&A each. Hopefully that works. I will be just making a quick sound for the last minute, so everyone knows, don't be disturbed. We'll start with Taman Rahman from Practical Action Bangladesh. I'm delighted to hear you talk, and yeah, please, the floor is yours.
Okay, so this is Tamana Rahman. I'm the thematic lead for the Climate and Resilience Change Ambition, and I'm based at Practical Action Bangladesh office. Practical Action is a UK-based international development organization, but we operate in many parts of the world, in South Asia, in Latin America, and in Africa. And among many of our areas of work, we focus a lot on climate resilience adaptation practices and a focus on early warning systems. So my talk will be briefly on what are the challenges and what are some of the innovations that practical action in Bangladesh is working on for an effective dissemination of early warnings to reach the last mile communities. So if I briefly talk about the context of Bangladesh, we all know that it's a highly vulnerable country to the impacts of climate change, and because of its location in the Bengal Delta and a very low-lying flat topography, the country is severely flooded. And we have 169 million population, and over half of our population, around 85 million, we are highly exposed to different flood risks. And with the changing climate, the increasing frequency and intensity of flooding is causing immense losses and damages with an increasingly high financial and humanitarian cost. So fluvial, pluvial, and coastal flooding, all three types of flooding are predominant in different geographies. And if we talk about especially fluvial flooding, which is the river-fed flooding, around 45% of the total population of Bangladesh is exposed to the fluvial flood risk. And if we look into statistics from the Ministry of Disaster Management and Relief from Government of Bangladesh, around 1.3 million households were affected because of this fluvial flood back in 2020, with an estimated damage of like 5,900 crore Bangladeshi taka. And globally, if we look into the investment in building resilience and reducing disaster risk versus post-disaster relief and response mechanism, the percentage is we invest 87% on disaster-related spending that goes into emergency responses, and only 13% towards reducing and managing risks. And in terms of Bangladesh, there is definitely lack of knowledge and vulnerabilities, and also the needs of the local communities and lack of capacity at the local institutional level is another barrier, which is hampering the proper implementation of flood risk management. So in terms of institutional framework for early warning systems in Bangladesh, we do have a very robust framework. So we have two ministries. One is the Ministry of Defense and one is the Ministry of Water Resources. And under these two ministries, we have the Bangladesh Meteorological Department and we have the Bangladesh Water Development Board. Those are like two hydrological and meteorological departments. And under these departments, we have other separate sector-specific departments like agriculture, fisheries. So the warning that is being generated by the scientific wing, which is the meteorology or hydrology department, it is disseminated through the different departments like agriculture, fisheries, and it goes directly to the local institutions and to the community. In theory, it looks great that we do have our system, but if we look again into the data, one of the Bangladesh Bureau of Statistics data from 2021 says that 66% of the disaster-affected households in Bangladesh did not receive an early warning in the year 2015 to 2020. And if I talk specifically about flood early warning, only 28% received the warning in 2015 to 2020. And when Practical Action conducted a study back in 2022, we found some major barriers that why these warnings that's being generated at the national level is not reaching at the local level. We found that there is a lack of better communication, there is lack of proper dissemination channel, and there is lack of authenticity of the information that is being delivered to the community level. So overall, if I summarize the strategic gap, there is definitely, in terms of dissemination, we do have a gap. And also we have a lack of effective interface or a mechanism to facilitate multi-sectoral coordination. We do have very interesting laws and policies and regulations. We do have the standing orders on disasters. We have disaster management acts, but in the field level, we do see some gaps of the proper implementations of the laws and policies. And there are very interesting approaches taken up by different organizations, different non-government organizations, different research partners, but those approaches are not being scaled up to a certain extent. So it is not becoming more sustainable and scalable. So what Practical Action is doing, Practical Action is one of the founding members of the Global Flood Resilience Alliance, and it is funded by the Zurich Foundation, and 8 different organizations are working as part of the alliance. We are operating in different parts of the world, both in developed and developing countries. And Practical Action is operating in 6 different countries. So in South Asia, we are working in Nepal and Bangladesh. And if I focus on Bangladesh, we are working in the South Central Coastal District, but we are expanding our footprint in also the coastal districts of Khulna and Satkhira. Currently, I'll be sharing our experiences from the district of Faridpur, which I have shown in the map. So what the Flood Resilience Alliance is doing, we have taken up a systems approach in understanding the resilience of the communities. So we have developed a framework, we call it the Flood Resilience Measurement for Communities, where we have incorporated different lenses of resilience. So we have incorporated the 5 livelihood capital. We have come up with the 4R lens. So if a system is robust, redundant, resourceful, or rapid. We have also incorporated the disaster risk management cycle, the different cycles, and we have also incorporated the 7 themes lens. And everything together, we have formulated this flood resilience measurement for communities framework. It's a framework and also a tool. It is a web-based and mobile-based tool. And there are 44 different indicators through which you can actually assess the existing resilience capacities of the community. And the assessment can be done through household survey, through focus group discussion, key informant interviews, and literature review. And everything can be incorporated in the web-based platform. So we have applied the tool in the community where we are operating in the severely flood vulnerable community. We have created different sources of resilience of the community, and we have identified some priority interventions with in consultation with the community. So if I give an example, the 44 sources of resilience I mentioned, early warning system is one of the 44 sources of resilience, which falls under like different thematic areas that I mentioned in the DRM cycle, in the 5 capital, in the 4R system. And when we went to the community, under each different sources of resilience, we asked specific questions in terms of structural barriers, in terms of social capital, in terms of their existing facilities of early warning system. So, for example, we have worked with 10 different communities, and in all the communities, we have identified the early warning system as a source of resilience got a very lower grade. So if we grade them from A to D, most of the communities got a C to D grade. So from these, since it's a systems-based approach through community participation, we identified some of the key priority areas out of the FRMC processes. And since we are prioritizing in the early warning systems, we started looking at what are the key elements of an effective early warning system. I'm sure we all know about the 4 pillars, the risk knowledge, the monitoring and warning, dissemination and communication, and response capabilities. But from our understanding, we have focused more on the dissemination and communication approaches, because this is something where we found that there is huge gap, and Practical Action as an NGO can contribute to filling the gaps. And we all know about the early warnings for all initiatives, that by 2027, every person on Earth should be covered by an effective early warning system. And in Bangladesh, out of the top, I think 30 or 12 priority countries, Bangladesh is one of the priority countries of this early warnings for all initiative. So if I talk about specifically pillar 3, which is warning, dissemination, communication, this pillar is led by the Department of Disaster Management, which is under the Ministry of Disaster Management and Relief in Bangladesh, and also the Bangladesh Telecommunication Regulatory Authority. So we are closely working with these organizations and making sure how best we can reach the last mile communities through different dissemination channels. So what Practical Action is doing, the early warning institutional framework that I mentioned, that the flood early warning is generated by the Flood Forecasting and Warning Center, and during our post-monsoon period, they actually are generating the warning. What we are doing is we are taking the warning and we are making it more contextual and disseminating to the community through different channels. What are the channels? I will describe one by one. So one channel is the dissemination of warning through mobile phone messaging. So if I talk about the literacy rate of the hard to reach areas or the most vulnerable areas, a lot of people lack they are not literate enough to read and understand a technical message. So when Flood Forecasting and Warning Center is generating the warning and sending it through their websites and everything, have I exceeded my time, or I still have some minutes?
You still have more than a minute, yes.
Okay, so what we are doing, we are extracting the technical message and we are making a very easy to understand voice message. And we collect the mobile phone numbers from the community, and through a blast server, we are disseminating the voice message to the community. So community people, they receive a voice call and they listen to the message and they take early actions based on the messages that is being disseminated. Our second approach is with the Ministry of Disaster Management and Relief. We have developed and launched a mobile-based application. It's called Disaster Alert for Bangladesh. It is available in the Google Play Store. So this application is more like you can get a warning through this application, but also before a hazard turns into a disaster, you can also take different measures through this application. The number of mobile phone users and the number of smart mobile phone users is increasing in Bangladesh. So this mobile-based application is also, to a certain extent, serving the community and also the local government stakeholders to take up a disaster warning and take early actions based on that. We have also established some digital weather boards, and the digital weather boards are established at the lowest tier at the community level, mostly at the union parishads. So if a community visits the union parishad's digital center, they can actually get 7 days weather forecast. They can also get alert for an impending disaster, and they can also get to learn different advisory services from the Department of Agriculture, and they can take actions based on that. And we have also developed a pool of local volunteers. We call them local resilience agents. So we are training them up how to get a warning, how to understand and synthesize the warning, and how to help others, those who do not have access to warning messages, so that people can get alerted and take early actions. So, and practical action is also working on—
Please come to a conclusion, please.
Sorry?
Please come to a conclusion, Taman.
Yeah, this is my last slide. So practical action is also working on disseminating agricultural advisories. So this is like a call center that we established with the Department of Agriculture. So I'll take any questions if you have, but thank you very much for your time.
So are there any questions? Please raise your hand. In the meantime, maybe I can ask a question. So you in the beginning, you talked about the challenges and yeah, there's a lot of different agencies involved, and obviously that's always a big challenge to deal with. And I was wondering, you were talking about the assessment you're doing of the existing resilience, and I was wondering who are you targeting with your results? So who is reading those assessments and who needs to take action? Is that a specific agency? Is that a specific group? Is that the weather service? Is that someone else?
Yeah. So when we are doing the assessment, I mentioned that we go to talk directly with the community through the focus group discussions and the household surveys, but we are also involving different government, local government stakeholders. So for example, the disaster management committees, the Department of Disaster Management. And we also do, when we collect the data, we grade the data and we do a validation with different stakeholders. So we involve the national government, also the local government. So they are aware of the process and the results.
Okay, thank you. So there is one question in the chat from Colleen Vogel. Very interesting work. And she asked, which groups are the most reluctant to work with you? You give an answer to that.
Interesting question. Yeah. I mean, I don't think anyone's reluctant, but everyone has their strategic priorities. So a lot of organizations are actually working on early warning dissemination. But the challenges I mentioned, that we need a comprehensive approach and like a cohesive platform. So I think these early warnings for all initiative is trying to do that. Yeah.
Okay, great. Thank you. So if you have any more questions, please feel free to use the chat, or then we can follow up with that. Okay, thank you very much. So we come to the next talk, which is by Miriam Murambadoro, and this will be recorded. So Isadora,
Perfect.
can you please? You have already started sharing the screen. Great, thank you.
Good day. My name is Miriam Murambadoro. I'm a lead scientist at the South African Weather Service. I'm here to share with you findings of a research that we did to understand the socioeconomic benefits that stakeholders in the health sector derive from the use of weather and climate information from the South African Weather Service. So I'll share with you an overview of the health system in South Africa. South Africa is an uneven health sector whereby 71% of the population is served by the public health system, which is funded by the government, and 27% rely on the private health system, whereby private hospitals and private medical aids contribute to the private health system. And the public health system is not well funded, and it often fails to address some of the past inequalities, as some people still have limited access to adequate health care in poor provinces like Limpopo and the Eastern Cape and KwaZulu-Natal. And most of the public hospitals are often understaffed, and as a country, we also still face the triple challenge of unemployment, inequality, and poverty, which increase the burden of, on the public health system, as many people are not able to afford private health care. South Africa's health system is characterized by an escalating burden of communicable and non-communicable diseases. And with the recent COVID, I think most people with comorbidities were highly vulnerable. And these are the people who were most at risk and got sick, and most of the deaths were could be associated with people who had comorbidities. And I think as a country, the number of people who died from COVID, I mean, it was quite significant in Southern Africa. In terms of the relationship between weather and health, health is one of those sectors that is sensitive to any changes in weather and climate, and it not only impacts on human health, but then also on animal health. The prevalence of pests and diseases, it's also linked to changes in weather variables, such as changes in temperature and rainfall. So outbreaks of foot and mouth, for example, and also the brown locust have been linked to the prevalence of extreme weather events such as droughts. So as the South African Weather Service, we've got a number of products, and we also undertake socioeconomic benefit studies to understand how the weather and climate information that we have, or the products that we have, can improve the lives or the ways in which some sectors operate, and also help them to become more climate resilient. So we undertake studies for different sectors, and the method that we used, for the health sector, we disseminated a survey online, whereby we targeted a number of stakeholders within the health sector who are working within hospitals, both public and private, those involved in research, and academia, and also those in pharmaceutical companies, a number of stakeholders along the health value chain. And we use the contingent valuation method to create a hypothetical market for weather and climate change information, as mostly weather and climate information are not for sale in South Africa, especially by the South African Weather Service, unless if you want particular products or data, then that's when a value is attached to it. But it's for this study, we had to create a hypothetical market for these products. And so the contingent valuation method allows for stakeholders to also express their willingness to pay for having, tailor-made non-market products or information. And, this would also help us understand some of the areas that they get to apply some of these products and information through, for example, mitigation of potential risks, strategic planning, advisory services, consultancy, and other uses. So for this approach, we created 5 bid levels whereby our users were asked to illustrate their willingness to pay and then choose the highest amount that they would be willing to pay for information. And the 5 bid levels were illustrated as below, but the maximum that people would be willing to pay would be about 1 million rand and above. The results that we got showed that there are a number of products from source, and one of the most important products from the weather forecast is the daily forecast. It's one of the key products that's very useful to stakeholders in the health sector. And then also the integrated relative health risk tool, which was particularly useful at the time that we undertook the study. It was during the COVID time. So it helped stakeholders to understand, the possible spread of disease, and then also help them to take the necessary measures. And so we also then asked our stakeholders to, give the perceptions of whether the information and products that they get from source were adequate to meet their needs. And 55% of the participants indicated that the products and information from source were not adequately meeting their needs in the health sector. And I just thought, let me just also highlight, some of the, benefits of the integrated relative health risk tool. So the tool is used to strengthen preventative measures and target mass screening. And particularly during COVID, this tool was adopted by the COVID-19 task team, and it was presented to the President of the Republic. And it was very useful to inform the allocation of resources in particularly poor communities where there was high vulnerability and also loss of income for those who were dependent on some of the economic activities that had been put on hold due to the pandemic. And so in terms of access to weather and climate information, the respondents indicated that about 54% of the males and 45% of the females do not receive any disease outbreak or pandemic advisories, which is quite concerning, considering that, for some of the pandemics, they were quite devastating and they would need to be managed early, especially in some of the communities where there were a significant proportion of the population that were vulnerable. And in terms of the platforms that are used to access weather and climate information, stakeholders indicated that they use the internet, phone applications such as AccuWeather, TV and radio to access weather information. And then for advisories, health advisories, they relied on the Department of Health, the Center for Disease Control, media and social media and television and the internet. But there were challenges with some of these sources of information. For example, with social media, is people tended to generate some information that was false, which made it very difficult to then take action, and hence there was always precaution that people would need to attach when they receive some of this information. And in terms of the benefits of weather and climate information for the health sector, they identified a number of benefits, which include, being able to then develop disease control strategies, and then develop health policy regulations, They would also use weather and climate information to do risk and vulnerability assessments at various levels, at community level and also at regional level. They were also able to use this to allocate financial and human resources. And then it was also used by pharmaceutical companies to to produce certain medical medication during certain times, dependent on what the information was providing. So, for example, during the winter months or during spring and things like that, they were able to respond accordingly. And then it also, weather and climate information is also useful, especially for emergency preparedness. And in terms of willingness to pay for information, respondents indicated that 68% of the respondents indicated that they were willing to pay for general weather and climate information from the Weather Service, and 32% indicated that they were not willing to pay for this information. And we also asked participants if they would be willing to pay for tailor-made products from the South African Weather Service, and 59% indicated that they would be willing to pay for tailor-made products, and then 41% indicated that they would not be willing to pay for weather and climate change information. We also then asked them to indicate which activities in the health sector they are willing to pay for, and the majority of the participants indicated that they would be willing to pay for information that would support research, and then also to mitigate and plan for potential risks. Those were the major activities that stakeholders would be willing to pay for. So we also asked participants to indicate the timescale of products that they were willing to pay for, and the majority indicated that they were willing to pay for monthly and seasonal information, and there was a fair number that was interested in hourly and daily information, and then also decadal, which include the climate change projections. There would be that would then help them to plan for future activities. And then we also asked respondents to indicate their stated preference amount, the highest, the minimum that they would be willing to pay for. And 62% of the respondents indicated that they will be willing to pay at most 1,000 Rand for weather and climate change information, and 31% indicated that they'll be willing to pay up to 10,000 Rand, and only 7% indicated that they'll be willing to pay more than 10,000 Rand for weather and climate change information. But now the costs of producing and maintaining the technical infrastructure that produces and stores this information far exceeds the highest amount that users are willing to pay for. And some users were actually indicating that they are not willing to pay because of lack of money, whilst others perceive that weather and climate change information are public goods that should be made available for public benefit, and they should be provided for free. Hence, the need for meteorological organizations to receive funding, public funding, to support some of these activities, the public good side of the services that they offer. So to conclude, we looked at some of the challenges and opportunities that are available for the Weather Service to take note of as we improve our offerings to stakeholders in the health sector. So firstly, what we noted was that the platforms that are currently used to disseminate weather information to the sector were a bit limited, and hence there's a recommendation to diversify some of the platforms that we use so that we reach more users in the health sector. And secondly, the needs of the stakeholders in the sector vary across the health value chain. So the needs of community health practitioners, medical health practitioners, and health insurance companies, they differ. And the way this information should be packaged for them would also be different. Hence, the Weather Service would need to improve its offerings such that it takes into account the different needs from the different stakeholders within the health sector. And thirdly, the information needs to be simplified to suit non-technical users, particularly those who are working at community level, who indicated that most of the information is provided in technical terms that are difficult for them to interpret further and assist communities. And also, most of this information is provided in English. And yet, South Africa is 11 official languages, and there's need to integrate some of these indigenous languages in the products that are or in the information that is provided, such that people are able to understand it and then also inform others. So there is a recommendation to make information that non-technical and then also use indigenous languages that would help to reach more users. Even those who are illiterate would be able to understand and also benefit from these products and information. Lastly, there is need to build capacity of health practitioners to utilize various products that are available. Many were not even aware of some of the products that the Weather Service has. The assumption was that, the Weather Service is just there to give weather information, what they see on TV and what they hear about on radio. But there's more that the Weather Service can offer, which would be useful or beneficial to the health sector. So there's need for the Weather Service to work with other stakeholders in the health sector, including the Ministry of Health, so that we can support stakeholders who are working particularly at community level to utilize the products and so that they are beneficial to the citizens. So that's my last slide. Thank you so much for your time. My contact details are below. If you've got any questions, please email me. Thank you so much. Bye.
Great. Thank you very much. So Miriam had to drop out quite on last notice, but thanks very much for providing us with the video. Very much appreciated. So if you have any questions, please feel free to email Miriam directly, or as Isadora said at the beginning, I'll be happy to receive questions via the conference email, and then we can forward that to her. Okay, so we come to our third presenter, Alejandro Godoy from National Meteorological Service, Argentina. Alejandro, the floor is yours.
Hello, my name is Alejandro, and I'm going to present the following work carried out by people of the National Meteorological Service of Argentina. And what I'm going to show you now is climate service co-production experience tailored to the hydro energy sector in South America. And this work was done with the Yacyretá binational entity, which is located on the Paraná River on the border between Argentina and Paraguay. As you can see in the figure on the left, the Paraná River is part of the La Plata Basin system, where millions of people live and important productive activities are carried out. Also, there are many cities near the coast of the Paraná River, and the hydroelectric plant is in the region marked with the red arrow. Also here, there you can see the location of the Yacyretá plants, and there is a photograph also. And what is the purpose of this work? The purpose of this work is the provision of relevant hydroclimatic information for decision making in the hydroenergy sector. And to fulfill this objective, it is proposed to show the co-production processes between both the institutions that led to the service currently provided. The co-production process is summarized in the following figure, which shows the different components of the work methodology for the co-production of climate services. The development of the service began with monthly meetings where we were able to define the needs and develop products for the sector. Also, it's highlighted that joint work sustained over time and feedback allows the continuous improvement of the service as is recommended by the World Meteorological Organization. And the next slide reflects the different components shown here. This work especially started with Carolina Cerrudo. Throughout the meetings that I show you, throughout the meetings, dialogue and feedback are encouraged, which allows the continuous improvement of the service provided. And once the user's needs were identified, first list of products was defined jointly, which was adapted and presented in the next meetings and in the continued meeting and presented until reaching the following catalog. Here are some examples of the catalog. Among the information provided, there is a summary of the seasonal and subseasonal climate indicators, as well as medium and long-term temperature and precipitation forecasts of greatest relevance for the user. And some of these products are processed and tailored exclusively for a boundary region of interest, as well as the La Plata Basin or the southeast of South America. And also a summary of the meteorological analysis relevant to the region of interest is also provided. This slide represents some samples of climate information adapted to the sector. The main variables that are important for the sector are temperature and precipitation, but they are presented through map of meteorological variables in which fields of anomalies and average values are shown. Both maps and information are in probabilistic and deterministic form. For example, in the left, you can see in seasonal forecast maps that were adapted to the region of interest to have a regional vision. Also, the weekly forecast shows the probability of precipitation greater than a threshold in the La Plata Basin, that is in the right. And that may have an impact on for example, and the height of the rivers, or also the possibility of extreme events also. And I'm going to focus in the identification of needs that we see. And one of the needs identified from the exchange was the availability of evaporation information. The user requirement was to have a water balance evaporation forecast information. So in this way, first we need to evaluate an evaporation forecast new products. Therefore, a soil model was evaluated, and evaporation data from station provided by Chassis are used to carry out the study. One of the preliminary results of this study was carried out through the big soil model. Here in the field of the left, you can see, for example, in blue, temporal series of the observation of evaporation in Encarnación, that is a city in Paraguay. In green, this is the big model simulation. And in red, you have the corrected big model with this observation that offer the users. Also about the statistical metrics that shows a significant improvement of the guidance of the corrected big without a correction. And the frequent period doesn't work as well as the training period that is in the right, but you can see, for example, the root mean square error is lower than in the big model, and also the correlation that is greater in the corrected big, for example. The strategies used to promote a continuous improvement of the service are, on one hand, permanent dialogue throughout successive meetings, and on the other, the elaboration of surveys to assess the quality of services and proposal for improvements. That led to a continued improvement of the service. In this slide is shown the structure of the first survey for users' evaluation of the service. For example, here you can see the sections, no? Different sections, the personal information, the overall evaluation of the service, the usability and utility of each product. And then when we have the results, we process the information. Here we can see some results of the user evaluation survey where the audience are specialists in hydrology. These results are shown in the figures on the left. Most of them say that the products are very useful and very clear. Regarding that, the product utility that is in the right, the product with the most utility are, for example, the ENSO actual state and forecast, also the trimester climatic trend, forecast of precipitation and anomaly, and also for the weekly forecast. The anomaly forecast for the different thresholds are also very important for the decisions. Other result, important result of the user surveys regarding the actions taken with the information provided are shown in the following table in the right. It shows the list of predefined actions that we proposed in the survey. But also other actions emerges in the comments, such as in the green box. For example, some actions are they refer to the maintenance of equipment, operation and management of the reservoir and navigability. You can see in the right, for example, here with different colors, the different products and the actions that contribute to you can see, for example, demanding planning, resources availability. So this is important to say also that the result taken into account are with more than 50% of the votes. So in summary, the most important conclusions, the present work shows the co-production process between the Yacireta binational entity and National Meteorological Service institution that led to the provision of the service that is currently provided in the monthly meetings. It is highlighted that joint work sustained over time and feedbacks allows for continuous improvement of services. For example, a soil model evaluation that also is a utility for us for the National Meteorological Service. The user evaluation showed that the products are clear and useful for decision making. Among the action most voted stand out the demand of planning, resources availability, organization of activities related to the sector, maintenance of equipment, operation and management of the reservoir and navigability. Well, thank you very much.
Thank you very much, Alejandro, for your talk. And are there any questions? I'll have a question. Sorry, with respect to this co-production process, Alejandro, is that depending on individual commitment of specific people, or in other words, are there any specific people who are driving this process, or is that an overall commitment from all the involved agencies? Can you say a little bit about that?
Yes, well, the people that is involved is the National Meteorological Service, that we define the surveys, and we in this meeting that we have these monthly meetings. Also, we have some feedback, no, that is very useful, no. But the most important person are from the National Meteorological Service. I think it's very important for us also to learn, no, how to adapt, not information to this special user that. In fact, we learned that the climatic information is very important for the planning, especially, no, because these hydroelectric plants need to define now the flow, no, of the river. So I think this idea for us is very new also. So we need to improve now in the future also.
Do you know if this hydro energy sector, are they using their own modeling or models? Are they doing like their own estimations, and are they doing their own calculations? Or is that depending on what they get from the weather service?
No, they use a lot of information from another weather centers. Also, they use information from Paraguay. For example, they have information of the nowcasting and weather forecast. The information is sent by Paraguay. So we focus on the climatic information. They're interested in the evaporation information for us because they can't do dust simulations. So they prefer that the National Meteorological Service do the job, no? So
Okay.
I think it's important. Yeah.
Okay.
I don't know.
Okay. Thank you, Alejandro. Great. So if you have any more questions, please feel free to use the chat, and Alejandro can have a look at that. So we come to our last speaker in this section, Gabriele Franch from Fondazione Bruno Kessler in Italy. Gabriele, please. Yes, we can see your screen. Perfect. That works.
Can you see my screen? Yeah. Okay. Okay. So yeah, I'm Gabriele Franch from Fondazione Bruno Kessler, which is a research center in the Trentino region, which is in northern Italy. And we have been working in the last few years with the local civil protection weather agency, Meteo Trentino, to build a fully automated regional early warning system. And we are here to share basically our experience with it. Okay, so let's say the overall picture is that especially the north of Italy during summer faces a lot of extreme events in the form of thunderstorms, hailstorms, lightning storms, and so on. And this trend is increasing in the last few years, and climate change projects this, let's say, this kind of events to be increasing even more. So the idea here was it came from the local weather service to have a completely automated system to try to have some kind of early warnings about this kind of events that are very localized in space and time. So they are very hard to predict from numerical models, for example. And to, let's say, also output a warning very quickly when something is developing. So the idea is to use nowcasting and to issue real-time alerts. And from the very beginning, the idea was to have a completely automated system that collects all the available weather observations and forecasts. So radar, satellite, lightning, ground stations, and also exploit, let's say, short-term forecasts to issue automatic messages, basically automatic warning messages. We also include, let's say, medium-term forecast, rapid update cycles. And we wanted from the very beginning to give the ability to the users of the system to be able to select the types of alerts, the communication channels, and the location, the area of interest. So the how, the where, and the what to receive from this kind of system. So the pros of a system like this is that you have a timely and possibly unbiased notification because it's not, let's say, forecaster dependent, it's a completely automatic. And the ability to specifically select whatever you want to receive based on your needs. So the type of alerts, the communication channels, and the area that you're interested in. What are the cons of such a system? We already knew it from the very beginning that when you're fetching a lot of live observational sources, you and issue alerts basically in real time, you have a possibility of high numbers of false alarms due to bad readings from sensors, due to all the things that may happen in real time, and you may not be able to manage. Quickly enough, let's say. Quality control of the input data, it's it's relaxed a little bit in such a system because of its own capabilities that you want to have, which is quick reaction time. So what do we have inside the system? The system is called SUMMIT, which is basically the Italian acronym for weather notification system, basically, meteorological notification system. We collect precipitation, wind, and temperature data from the regional stations, from different entities in the region, and from the nearby regions, both managed by the Weather Service and also from crowdsourcing. So we also have crowdsourcing data coming in. We have lightning strikes from the Italian Air Force, radar data, and mosaicing of the radar data with the nearby radars at very high frequency and high resolution. And then we have also forecasting sources. So we have our own forecasting system, AI based on artificial intelligence for precipitation forecasting, and the numerical models, both, let's say, up to 4 days, a European model, and the rapid update cycle for the local area model. So we have a lot of stuff coming in. Just talking about a little bit about our own forecasting for precipitation. We're very interested in the forecasting of thunderstorm cells. We use an AI-based system, so it's a deep learning model that forecasts precipitation up to 100 minutes. We use the first 45 minutes at the moment for alerting purposes. And it's run at a very high resolution, so 500-meter resolution based on the radar data, and it's updated every 5 minutes. So every 5 minutes we compute the next hour and a half of forecasts, and based on a 500-meter resolution grid, we compute the location and tracking of possible thunderstorm cells, and then we use that to eventually issue alerts on the areas. Where are we calculating all these alerts, and what are the alerts that the system outputs? Well, we have 3 different possible, let's say, areas we use for anything that it's computed all over the territory. We use catchment areas. We use the catchment areas at the highest, most granular level. So we divide our territory in 405 areas. Some of them are very few square kilometer in areas, in size, let's say. And we compute both accumulations of precipitation and other things that may be interesting that are happening in each one of these areas pretty much every minute. Okay, then we compute also some alert directly based on weather station data observed, and other things like lightning strikes are basically location-based, point-based alerts. We have both alerts on forecasts, let's say, so both on the forecast that we use, then that also on observation. This may seem counterintuitive, but also giving let's say, timely alerts on observed things that are happening. It's useful for, let's say, for many applications. For example, if you send a message that it's starting raining in a specific location, even if the thing is not a forecast because it's something that you're sensing right now, that it's starting happening right now, it's already very useful for example, I don't know, route management, knowing that that snow is starting at this very moment in a specific location. So both alerts based on observation sources directly, then also the one on forecasts, have been proven to be very useful for this kind of systems. We are trying to mitigate, let's say, possible anomalies. So with a 2-stage anomaly detection system, the first stage is completely automated again, where we use basically historical data to train an AI system to check if the currently sensed data from the observational sources is too anomalous. In this case, the source is automatically disabled some time, basically. So if there is something that really goes off in some observational sources, it's automatically filtered by this system. At the end, whatever, let's say, whatever anomaly detection you have, you end up having some alerts calculated, so some outputs that is going to be sent to the users of the system. And before sending it out, we still put it into a queue, which is basically a Telegram channel, so a chatbot channel, where the messages stay there for 3 minutes. And there is an opportunity for human reviewers, so for forecasters, to, let's say, dismiss the alerts if they think there is a false alarm. And if no action is taken, after 3 minutes, the message is considered valid, and it's automatically released on all the distribution channels. As we said, we are using multiple distribution channels. So the same exact information is delivered through 3 different platforms. One, it's a mass alerting platform, and that it's open to the public. Another one, it's an overview web map, so a web-based application where everyone can go and see what's happening all over the territory. And the other one, it's a Telegram chatbot, so it's a personalized experience for most advanced users. What is, let's say, the typical user for each one of these distribution channels, the typical users that we envisaged? For the Telegram chatbot is the one that has the fullest degree of customization. You have the ability to filter the alerts that you are interested in at the most granular level, down to a single station, single location, and single type of alerts that you may be interested. So the typical user there, it's, let's say, the technicians or a domain expert or an enthusiast, let's say. While on the very other side, there is the overview map. You open a website, it's an anonymous access, so everyone can access it and see all the alerts that be generated by the system. They are categorized by, let's say, they have a very broad categorization into 4 different categories, and you can check what's going on, basically. And this is useful also for people that may want to take this alert and automate and have a downstream automation of this kind of information. So they want to pick up the data that is going out, that's coming out from the system, and then to process them.
Last minute.
On their own. And then we have the mass alerting platform, that it's a streamlined setup that we specifically developed for citizens. I will skip this slide. This is basically the flow for the mass alerting platform. Basically, we just require the what, the how, and the where, and you are done, and you can receive the alerts on the channels that you want. To sum it up, so our experience so far, the good thing about this system is that we got a very good feedback about having a real-time system that it's completely automated. It also reduced the forecasters' fatigue a lot, because we can redirect users to these systems, and forecasters are relieved a little bit. Then the 2-stage anomaly detection system helps a lot in reducing false alarms we've seen. And the multi-delivery channel works. So the same information delivered on a different channels, on a different delivery medium, really caters to different audiences we've seen. What is the bad thing? This is intrinsic to the system. No matter what, you will have false alarms with this kind of setup. So we have to be upfront with the users of the system that a certain degree of errors are going to happen. Even worse are false negatives. So an alert should have been emitted, but it didn't, because, for example, the radars were not working at the moment, stuff like this. These are even harder to detect and mitigate. We still are working on this to try to find a solution. The ugly part is the one that we could have done better for the very beginning, so that we would have liked to, if we have to redo this from scratch, we we would have done better, is that users should be able to provide frictionless live feedbacks about the system. So being able to give a feedback about this message has been useful for me or not. We still don't have this in place, so we plan to do it. And the other thing is that setting up a multi-delivery platform is technically, let's say, not easy, okay? And so a proper assessment has to be done before committing into new distribution channels, okay? So thank you. If you have any questions, I'm more than happy to answer.
Thank you very much, Gabriele, for that interesting talk. Are there any questions? We're running a little bit late, but I think we still have some time for that. So there's one in the chat from Sarah Jenkins. Really interesting talk. Have you had any specific feedback about how false alerts are received by the users? If so, does this differ across platforms? And are users typically forgiving?
That's that is a very interesting question, because the automated the two-stage both automated and human review, let's say, false alarm reduction system that we set up. We set it up after feedbacks from the users. When we really opened up the third delivery channel, the one for the users, let's say for the public, the mass alerting system, we received feedback from people writing emails to us that the system was had too much false alarms. And so we really doubled down on let's say the reduction of false alarms when we opened it up to the citizens. Retrospectively, we should have done this earlier, both the opening up the system to the citizens, because it was for a couple of years only internal for the forecasters and, let's say, other civil protection agencies inside the public sector. We would have done this earlier. So yes, now let's say the system, it's let's say it's good in at least we don't receive so many complaints anymore. We have seen that being upfront about the fact that the system may have false alarms and will have false alarms, it's useful also. So when people expect it, then they are also much more forgiving about it. Okay.
Great, thank you. So I don't see any further questions, so maybe I have one. So you mentioned the false alarms as one of the major challenges with coming into a fully automated system. Are there more? Or, I mean, false alarm is a big thing, obviously, and this is connected to this different or other challenges, obviously. But have you encountered any other challenges which were new to you using an automated system?
Well, the biggest one was for sure the false alarm, because we were expecting it. The other thing is that, let's say, especially when you're trying to do things as much as you can in real time, the harmonization of all the incoming data sources is not easy at all. Okay, you have to be very careful of let's say the failure modes of observational systems. It's way wider than we expected. Okay, this is may seem obvious, but until you put all of them together and you see also some alerts depends on multiple observational systems to be working correctly. So this increases exponentially, let's say, the possibility of some kind of false alarms, and so you have to be very careful about it. Okay.
Great, thank you. And maybe last question: is that published, that work? Can you read about it, or is that anything?
We still don't have a publication. We're planning to do it. So this is, let's say, our first international presentations of the system, to be honest. But now that it's open to the public, we're going to have write a publication about it. Yes.
Great, looking forward to that. Thank you very much, Gabriele, and thank you to all the speakers. And I'll hand over to Carla Mooney for the last part of our session.
Thank you very much, Thomas. And thank you to Isadora for the earlier part. So this is just going to be a shorter section now, and I appreciate everyone is still online, and we've had a really diverse range of very interesting talks. So it's really good to keep going along. So we're just going to have 4 short talks and maybe 1 or 2 questions about each talk, and then look forward to moving to Gather Town to have the opportunity for some more informal discussion. So the order of the talks is going to be Lizzie to talk first, Johannes, Francesca, and Kathrin. So Lizzie, if you would like to share your screen and proceed to talk. Thank you.
Okay, hello everyone. Yeah, I'm Lizzie Kendon. I work at the UK Met Office and also at Bristol University in the UK. So I'm delighted to present the Represa project, which is all about building resilience and preparedness to tropical cyclones over Southern Africa. Okay, so this is a project that's led by myself, Professor Engelbrecht at WITS in South Africa and Professor Luis Artur in Mozambique. It is funded through the CLARE initiative by IDRC and FCDO. Now, Mozambique, Malawi and Madagascar are the kind of key focus of Represa, and these are countries in Africa that are very vulnerable to the impacts of landfalling tropical cyclones. And yet early warning systems are really not adequate currently to prevent serious loss of life. So there's an example here back in March 2019, the tropical cyclone Ida made landfall in Mozambique, and more than 1,500 people died in the path of the storm. Hundreds of people also died because of a significant storm surge and river flooding in Beira itself. So the impacts of tropical cyclones are multi-hazard, and this is not well reflected in current early warning systems. And in addition, despite the real vulnerabilities of this region, very little is known about how tropical cyclones might change in the future, and therefore whether early warning systems are resilient to what we might expect in the future. So Represa is a project focusing on the impacts of tropical cyclones in a changing climate in these 3 countries, really trying to address the region's vulnerability. So it takes kind of novel modelling right through to early warning systems and onto decision making at both local and national scales. So there are kind of 4 main objectives, and I'll just briefly go through these now. So the first is about actually quantifying what the changing attributes are of landfalling tropical cyclones. So this will be using kilometre scale modelling, both in the UK and in Southern Africa, to really kind of gain novel insights into how changes might look in the future and whether we might get unprecedented events. The next objective is about actually assessing the flood hazards, both now and into the future. And this will be including the compounding effects of surface water, river and coastal flooding, taking inputs from kilometre scale models to really provide new insights into flood hazard. Then there's objective around strengthening multi-hazard impact-based early warning systems and their uptake in vulnerable communities. And I'll talk about that a bit more later. And finally, about formulating adaptation options that enhance resilience in these vulnerable communities. So Represa is really taking the research right across timescales. So it's both on the early warning side and right through to long-term adaptation. So Represa is made up of 4 work packages that essentially align with those 4 objectives that I've just briefly outlined, and then has a living lab approach in terms of how we achieve research for impact. So we have 5 living labs kind of outlined in the points on the star here. So I'll just talk through these very briefly. So the first Living Lab A is all about the design and dissemination of early warning messaging to ensure this is accessible by vulnerable communities. Living Lab B is all about improving the capacity of the national mandated agencies for multi-hazard impact-based forecasting. Living Lab C is about stress testing humanitarian action plans so that they are resilient to changing climate and vulnerabilities. Living Lab D is about creating organizational plans that are sensitive to conflict, migration, violence, and changing climate hazards. And then finally, Living Lab E is about the co-development of adaptation plans that are sensitive both to climate and changing vulnerabilities in these regions. So the Living Lab approach is a major part of REPRAISA, and that's being led by the Red Cross Climate Centre. And this is a method whereby people are brought together, so stakeholders, practitioners and researchers are brought together to address a key issue. So in REPRAISA, the way it works is that the work packages themselves are kind of the research engine, so they will be producing new data and are kind of identifying the key research questions that then need to be taken into the communities, with community-based research happening in each of the 3 countries that are focus of the project. And then that will be taken through into the Living Labs, whereby these issues will be tackled at an institutional level. So one of the first tasks that we've been doing within REPRAISA is carrying out a baseline assessment of early warning systems. And this has identified a number of gaps and limitations. So the first of those is around a lack of multi-hazard warnings and the consideration of compounding and cascading impacts. Also the fragmentation of different types of early warning systems and areas that have limited access, for example, those impacted by conflict. There are also a number of different institutions who are responsible for early warnings and the various components to that in the different countries. And there are issues with the coordination and the data sharing across those institutions. There are also barriers to the communication and understanding of warnings. And finally, the changing risks due to our changing climate are not currently captured in the design of these systems. So within REPRAISA Work Package 3, which is specifically about trying to improve multi-hazard early warning systems and their uptake in communities, is carrying out kind of key research to try and improve our understanding and also understand what the issues are for, particularly a key concern, I guess, is the effectiveness and efficacy of early warning systems in some of the most vulnerable, marginalized communities. So the key question for Work Package 3 is what multi-hazard early warning system do vulnerable communities need to build resilience, and how do we design or improve these? So a number of sites have been selected in the 3 countries, which are based on communities at risk, but also we'll be revising that in the context of future hazards and changing hazards. So there may be communities that currently aren't impacted, but maybe in the future, and that will be taken into account as well. And then, so interviews and questionnaires will be used in community-based research to understand both the perception of risk, how the community see the value of the early warning chain and what their current needs are. So the methods that we'll be employing include interviews, participatory action research, so community mapping, storytelling, that type of activities, and also surveys will be used particularly to target some of the more vulnerable groups. And we will be considering how early warning systems function within a kind of complex system framework. So, you know, what systems do communities depend upon and how do they relate to each other? And is there any evidence of anticipatory governance? And as I said, a key focus of REPRAISA is on the vulnerable communities impacted by violence and conflict. So in Work Package 3, which is all about early warning systems and improving their uptake, there'll be a number of components of the work there, but basically there'll be a hazard assessment including taking the new information from the kilometre scale modelling and the flood modelling in Work Packages 1 and 2, assessing vulnerability and exposure both through kind of existing reports and proxy indicators and community-based research, and then considering this within a complex system framework and looking at anticipatory government. So here we're talking about, people who are making decisions on behalf of vulnerable communities, and it's really important that they are able to respond to changes. So that in this case, that might be changes in climate, and therefore the need to potentially adjust early warning systems. And it's really important that that reaction is anticipatory. So, there needs to be a blueprint for how we see climate change impacting the region, and that can then be used to inform decisions. And just finally, I wanted to very quickly just run through the Living Labs approach, which is very key within Represa. So this is about bringing together practitioners and researchers at an institutional level to really tackle issues. So it is a dialogue, and it's kind of demand-led. So the particular issues that need to be tackled come together. So it's a research-based process bringing together people. It's a dialogue. It's an environment where multidisciplinary questions can be tackled and discussed, and people are able to bring in their own understanding and observations into the process. It's socially interactive, so it's accessible, and it's culturally responsive. And importantly, it's transformational, so it disrupts power structures, and it aims to achieve sustained partnerships that help us to address key issues. And what does the success looks like? So here are 3 points. So it challenges assumptions, it can achieve technical capability development and behavioral change. So in the context of Represa, and so technical capability development. So one of the things that success may look like in the context of our project is really improving the capacity of the national authorities to carry impact-based multi-hazard forecasting. Also, we're wanting it to improve the kind of institutional practices in terms of early warning system and adaptation planning, so that ultimately we achieve the goals of improved resilience in the region. So with that, I'll stop there. Thank you very much.
Thank you, Lizzie. That sounds a very comprehensive and ambitious project. Just wonder if anyone has any questions they'd like to ask. So I'm interested in the Living Lab approach. I mean, because the theme of our conference is the role of social science in achieving the early warnings for all initiative. Is there a specific reason you chose that approach?
So I think this approach has been used very successfully in the past. So it's led by the Red Cross Climate Centre, and it's used to really bring people together. And I think it's this co-production of plans and information sharing that is so critically important and ultimately successful in trying to achieve change. Yes, I think that's the reason we selected it. We felt that it was, a very powerful approach that's proven to work and is bringing together all the different actors, which is really essential here.
Thank you very much, Lizzie. I hope that you can join us in the in Gathertown, so we might be able to have a bit more of a conversation there. Thank you very much for presenting. Okay, so Johannes, I think you're going to speak next.
Yes, I will share my screen. Thank you for the opportunity to present Meteorology and discuss our priorities and goals within the next few years, including our contribution to the Early Warnings for All initiative. So let me start by briefly introducing Meteorology. You can also have a look yourself by scanning the QR code. So Meteorology, established in the mid-2000s, is a flag program of EUMETNET and now garners hundreds of millions of clicks annually. It serves as a comprehensive platform for impact-oriented hydrometeorological warnings across all of Europe, and currently 38 European national meteorological and hydrological services provide the warnings to Meteorology in 34 different languages. Meteorology's success lies in its simple 3-color code, which offers the public a clear overview of the awareness situation in Europe, and this allows for consistent and coherent interpretation throughout the continent. By visualizing the current awareness situation and offering impact scenarios and advisories, Meteorology empowers individuals to stay informed and take necessary precautions to mitigate risks. Additionally, all warnings are provided in an aggregated way as feeds, making them accessible to all global redistributors like AccuWeather, Apple, Google, Microsoft, Weather Company, and many more. And this facilitates the dissemination of warnings and integrates them into everyone's electronic devices used daily. Meteorology is also recognized as a best practice by institutions like WMO and World Bank, and serves as a role model for Jiménez. And since its initiation, Meteorology has been managed by Choose for Austria, the National Meteorological Service of Austria. So within the next 5-year strategic phase, one of the key priorities of Meteorology is the RODIO project. The main objective of this project is to create a centralized access point where all meteorological data sets designated as high-value data sets under EU regulations are freely accessible to everyone. And Choose for Austria, representing Meteorology, leads the work package concerning warnings, which consists of 4 main tasks. So warning coordination includes the comprehensive support of members and the coordination of their warnings. And by implementing new CAP read-in routines, expanding the use of hazard types, as well as providing warnings up to 5 days in advance, we aim to further increase the availability of our warnings. Enhancing the Meteorology CAP profile and establishing a dedicated expert team on impact-based warning will improve the quality and harmonization of the warnings provided through Meteorology. And all warnings will be provided by newly developed APIs, which will be integrated into already existing Meteorology services and make the data accessible on the centralized European access point. And besides the work in the RODIO project, we have identified 6 key priorities we want to focus on in the next 5 years. And we will focus on enhancing support for our members by improving communication channels and addressing issues promptly. Additionally, efforts will be made to engage with redistributors to understand their needs better and integrate them into our system effectively. Documenting good practices and fostering knowledge sharing among members will also be a key priority for us. An expert team, as mentioned, dedicated to impact-based warning will be established, aiming to raise awareness and enhance provided impact data. Ensuring Meteorology's resilience and future readiness through technological advancements and increased server capacities will also be emphasized. And lastly, exchanging information with the multi-hazard domain and collaborating with organizations like the Emergency Response Coordination Center will remain important for staying updated and fostering synergies in the early warning ecosystem. And as an essential warning dissemination system covering 38 countries in Region 6, Meteorology plays a critical role in the success of the Early Warnings for All initiative, especially in Pillar 3, Warning Dissemination and Communication. And we aim to support countries in Region 6 that are not yet Meteorology members or covered with warnings, so sharing good practices and knowledge accumulated over almost 2 decades. And there are already several of those countries interested in joining Meteorology, and we will support them in doing so as much as possible. And by using the extensive network of Meteorology and its redistributors, these countries will be able to reach the targeted audience directly and effectively. We are looking forward to contributing to this initiative and increasing impact disaster preparedness and response at national, but also international levels, ultimately saving lives and contributing to a safer and more resilient society. So many thanks for your attention. If you have any questions, please feel free to contact me anytime.
Isadora, you've got a question.
Yes, and particularly on the role of these redistributors, and which is your experience on how the information is transformed from what Meteorology is providing and what these redistributors are sharing? Is the same information, or do they give other values of communication?
So we're in close contact with our redistributors, and we have frequently meetings with them so that we can somehow align what they will present in their applications. But of course, there are some difference on how they visualize our warnings in their applications, but we try to somehow harmonize also their ways in presenting information. And we have some guidelines on what they should present, and actually they're not allowed to change or edit any of the information we're providing to them. and I think they're also not interested in doing that. So yeah, I think we're in a good way, in a good situation for that. Yeah.
I mean, my question is a little bit about, you're bringing 38 countries together to present something consistently. I'm very curious about how do you achieve that consistency of the alert level from all these different countries into one platform?
So it was quite a long process over the last 20 years, and we have established the meteor alarm awareness levels. So we also have yellow, orange, and red, also meaning moderate, severe, and extreme. And all the members are providing this information within their CUP warnings. Yeah. Of course, it still kind of depends on the resources of the weather service, if they actually have impact data to base the awareness level on. Some have thresholds, some have impact data, but we're also working on this within the impact-based warning expert team in the future. But it's quite an effort, actually.
Thank you. Yeah, I believe it. Yeah, thank you very much. That was an interesting talk. I hope you can come together, Tantu, for an ongoing discussion. Now I was going to call on, someone's just asked in the chat if these are the lightning talks, and yes, they are. So Francesca, I think, is going to speak now about EUMETNET, and forgive my pronunciation.
Yes, good morning to everyone. My name is Franziska Schmid, and I'm working at Geosphere Austria. I will try to share my screen now. Yeah, I will shortly present the EUMETNET Nowcasting module to you and some of its outcomes. First of all, you have heard already a bit about EUMETNET by Johannes with the EMMA project. EUMETNET is standing for the European Meteorological Services Network, which was originally created in 1995. So it is, in the meanwhile, a grouping of 33 European national meteorological and hydrological services who are the members. There is an assembly and advisory committees to oversee all of the EUMETNET's undertakings. And EUMETNET is a framework to organize cooperative programs between members in various fields of meteorological activities. And the members who participate in funding a program, they share both the costs, but also the benefits of the program. And 6 programs are related to forecasting. You have heard already a bit about the EMMA project. The link is included here too. Then there's another one who provides training to the forecasters, the EUMETCAL program, the CSNWP, which is coordinating the numerical weather prediction consortia, and another one about the ensemble prediction systems to build very high resolution ensemble systems in Europe, and the post-processing module, and last but not least, the nowcasting module, including also very short range forecasting and seamless forecasting. And I'd like to focus on some dissemination and communication achievements in this module. We initiated a special issue about seamless prediction systems in the journal Meteorologische Zeitschrift. 11 articles have been published there. I have included the links in my presentation, so you can watch them up later if you want. We organize every 2 years the European Nowcasting Conference, which is a platform for scientists, forecasters, and users from applications to exchange information, hold presentations and discussions. I have also included some links here. And in addition, we organize also some series of lectures as another possibility to exchange information between Met services. And we have also elaborated surveys for the Met services, but also for their users, to gather information about user groups, observations, use of probabilistic products, ensemble forecasts, impact forecasting, and seamless systems, and also the added value of all these systems in the verification and training, the communication and visualization aspects, and the transnational cooperation. So you see that these surveys were really big. We were gathering a lot of information, and this is maybe also Yeah, and in the next step, I would like to focus on the communication and visualization aspects. We had two surveys, as already mentioned, one for the Met services and another one for their users. Both had a lot of questions, while probably the responding rate was not that high. The Met service survey had 47 questions, and the user survey 39 questions. The NMHS survey was distributed amongst the Nowcasting module team, and the user survey was distributed by the respective Met service with its users. And I would like to focus on some results of the surveys. Two results of the Met service surveys are shown here. One question was, how do you provide nowcasting information to the users? And you see that most of the respondents use for the visualization maps or graphs. But it is also important to provide timely updates of the products and that the information is tailored to the needs of the users. And the Met services were also asked what they think about video explainers in advance of high impact events. And you can see that 67% say that it could be useful and 33% said that it is very useful. When we go further to the answers by the users, we see the following. One question was, in which tasks do you need weather forecasts and warnings? So mostly they need weather forecasts for the everyday planning, but also for the preparedness in case of a special weather situation and for operational duties from minutes to a few hours ahead, but also for the long time planning. And when asking which kind of problems do you encounter when weather warnings are presented, they respond that too many warnings make a dulling effect, or it can they cannot pay attention to all of these warnings, but also that they have the problem to deal with the uncertainty in weather forecasts and warnings, and there might be an inappropriateness of warnings with respect to geographical characteristics of warning area. And when asking the users which kind of communication tools do you use to get information about severe weather development, most users answered that they use websites, but they also use email and phone. Another question was about the quality of weather information on social media. Most of the users think that this information is worse compared to the weather information from the Met services, but a major part also says that this is complementary. And also the users were asked about these video explainers and in advance of a high impact weather event and if it could be helpful. And most of the users said yes, to understand the impact of the upcoming weather and to improve their general weather knowledge. Yeah, some also said no, or I don't know. This is my last slide. We have published most meaningful results of the surveys in these two papers. And we have an ongoing cooperation with colleagues from South America, from WMO, about the survey. So it has been adopted and translated to even more languages. And survey results are also available for many parts of the world for the different WMO regional associations 1 to 6. And I have included a link here. You can see the results. And also a paper is in work. And with this, I would like to thank you very much for your attention and close my presentation. Thank you.
Thank you very much. That was very interesting. I think that Isadora has provided a link to the paper. Would anyone like to ask just one question? I'm aware we're getting pretty late into time. I guess my question would be, is the survey checking into the uptake of the research findings from the project?
Yeah, it is one very big output of our program.
Yes,
so we
yeah.
are using the cooperation of all the European Met services. And but as I said, the answering rate was not that high because maybe the surveys were really big. So when
Yes.
we would redo a similar survey, we would probably focus on one part and make more surveys, you know, not only one including all the different aspects which are relevant for nowcasting, but maybe one focusing on observations, another one on the systems, another one on the communication. Yeah.
Yeah, yeah. Okay, that's a great point. Okay, thank you very much. We've got two more short talks. One is from Kathrin Wapler and one from Priscilla Sosa. So, Kathrin, can I call on you to share your screen?
Good morning, everyone. My name is Priscilla Sosa, and I'm part of the work team of the Department of Meteorology and Society of the National Meteorological Service of Argentina. In this instance, we will present part of the actions developed by our institution in recent years to strengthen the interactions with users of official information, resulting in a collaborative document entitled Good Practices for Interactions with Users of Meteorological, Climatic, and Environmental Services. Over the last few years, interactions with users have become a central topic of the institutional agendas aimed at improving meteorological and climate services. Internationally, different frameworks and guidelines have highlighted the importance of inter- and transdisciplinary collaboration in delivering user-centered services. This document we are presenting was part of the Strategic Plan 2020-2023 of the National Meteorological Service of Argentina. And this plan emphasizes the importance of tailoring services to meet users' needs, facilitating informed decision-making, and enhancing the entire value chain of meteorological, climate, and environmental information. So here's an infographic that captures the main idea we want to get across about how we deliver these services. Instead of just giving out information one way, we're suggesting a continuous interactive cycle where everyone's input is key to making our products and services better. This proposal lines up with the WMO guidelines to transition from a linear model of meteorological and climate information to a relational perspective, emphasizing the need to involve a multitude of stakeholders during the different stages of the co-design, co-production, and co-implementation processes. Furthermore, these interactions offer many benefits. Customized service delivery to make user-specific needs, enhanced decision-making capabilities, and fortification of the entire meteorological and climate information value chain, the promotion of a co-production mindset, fostering improvements in processes, products, and services, and strengthening of institutional organizational capacity, resource optimization, and strategic planning for government initiatives to mitigate hazards and unprotected and exposed populations and risk environments. So our agency has undertaken the production of this guide document. This publication analyzes the current state of interactions between internal and external users of the institution and systematizes a series of methodological tools, lessons learned, and good practices for the involvement of users with an interdisciplinary approach. It's organized by chapters. For example, the first one of the initial diagnosis analyzes the current state of our institution. based on a survey conducted in 2021 on the interaction of its departments with users from different sectors that use meteorological and climate products and services. The second chapter suggests strategies for gathering and structuring relevant data. The third chapter presents methodological tools for addressing and engaging with users based on features of the target audience and the types of user needs. And finally, the last chapter provides recommendations for the analysis of the information obtained and its results to facilitate evidence-based decision-making. Our initiative started with surveys, workshops, and interviews involving personnel from each department. Based on this research, we developed a diagnostic report on the interactions between these departments and users from weather and climate information. We used the social network analysis methodology to map all the interactions within the institution into a single network. Through this effort, we identified and characterized the internal and external users from each department according to types and patterns of interactions, and structured them and structured the information in terms of work teams, resources, objectives, links with other departments, and more. In the second chapter, we take the strategies for approaching users suggested by the WMO, starting from the 4 cyclical pieces that are user participation and partnerships for the development, design, the delivery, evaluation, and improvement of the service. So to define user needs, there are different ways users interact, from active to passive. Some are customized and focused on the user's needs, using direct relationships, while others focus on the provision of information through web pages or apps or platforms in general. In chapter 3, these tools are described in detail, trying to show the advantages and disadvantages of their use, the intensities and types of users for which they can be most useful, with the intention that each team can build a specific approach strategy that is the most convenient and the best suit to each project and the stakeholders that they are working with. These tools are divided into those that are used for data collection, such as the interviews, surveys, workshops, to gather information directly from the stakeholders, and those that are used for information analysis, such as key actors mapping that helps to identify project stakeholders, their relationships, and their roles, the SWOT to detect strengths, weaknesses, opportunities, and threats, and the results reports that provide a summary and interpretation of a survey or study findings. Well, to conclude, in summary, we believe that this material allowed us to share a fresh approach in the field of meteorological services to strengthen co-production with the stakeholders through specific strategies and work guidelines. Also the importance of interdisciplinary and intersectoral collaboration to ensure meteorological and climate information is socially relevant to decision makers in line with their uses and their needs. Lastly, highlighting the value of including social science perspectives. These sciences play an important role in integrating social approaches within scientific, technical, and governmental organizations leading to improved community services.
Thank you very much. I don't think we've got time for questions, but I do.
Okay.
I'm going to be sneaky and have one question, which is, you know, your good practices publication. Is that available in English?
Yes, yes, we have it translated into English as well. Recently, very recently, we have the
Fantastic.
document in English.
Okay, brilliant. Thank you.
Yes,
Thank you so
we will share it.
Oh, great. That's fantastic. Okay. So lastly, we would just like to ask now Kathrin to speak on one of my favorite topics, which is evaluation. In fact, how do we know we're doing a good job?
So the main question of our work is how to best evaluate and communicate the value of severe weather warnings. We all think that severe weather warnings are certainly really important, but we want to really estimate the value and communicate it. So to tackle this issue, we set up a survey and ask you, all the participants of the conference, to contribute to the survey, because you've got expertise in various relevant fields. So feel free and happy to contribute. So, but let's not talk about weather for a couple of minutes. I want to tell you a quick story. Imagine the following situation. We've got a bicycle shop with a shop owner and a customer arriving. So the shop owner asks, what are you looking for? The customer certainly is looking for the best bicycle, otherwise he wouldn't be there. So the shop owner starts to suggest bicycles. This is the best bicycle. Well, the customer isn't really is a bit confused. So what should he do with this one? Well, this is really special. I think it's not good for me. Do you have another one? What about this one? This one is very unique. Now the customer is even more puzzled. What should he do with this? This one might not be suited for me. So how do you want to use the bicycle? Well, I want to go fast from A to B. Ah, okay, so this bicycle could be suitable. Well, this bicycle could be suitable as well. And maybe this bicycle could be suitable as well. Or even this one. Well, we don't know whether the shop owner is successful in actually selling a bicycle. The next customer arrives. So this time the shop owner already asked two questions. What are you looking for? How do you want to use the bicycle? The customer is obviously looking for the best bicycle. He wants to use it for shopping. So the shop owner knows, oh, I've got two options for you. These bicycles could be suitable. Well, again, we don't know whether he was successful in actually selling a bicycle. We hope so. Afterwards, the shop owner starts thinking, well, what characterizes a good bicycle? I don't know. Maybe I should ask. So he asks all his customers what characterizes a good bicycle. And he gets lots of answers, lots of different answers. A good bicycle should have a nice color, should be safe, fast, low maintenance, comfortable, flexible, robust, cheap, whatsoever. So the take-home message for the shop owner now is, depending on the definition of a good bicycle, different measures are useful. Well, am I telling you something about bicycles? Isn't this a weather conference? Yes, it is. So let's talk about the weather again. Depending on the definition of a good weather warning, different measures are useful. Well, and this is even just part of the story. This was just a quick intro into our topic. So if you're curious about what other aspects are there to the story, click on the link, contribute to our surveys. Thanks to those who already contributed. We've got 61 answers, I think, so far. But I wasn't sure whether we've got enough answers up until now, so I decided to give just a quick intro, but I will be in Gessertown and happy to share the first results that we've got from our survey.
That's very good. Thank you so much. I think that's a good segue for us to be thinking about going to Gathertown now. Just want to thank everyone who's presented in this session. It would be very nice if we could all actually stand up and actually walk to a conference centre and share a glass of wine or a cup of tea, but unfortunately we can't. So we're going to have to do it virtually. So just again to thank the other conveners of the session, Isadora and Thomas, and all the wonderful presenters. I think that we have a big challenge to synthesize all this great information into a meaningful output from the conference. And I guess that's a piece of work we'll be looking forward to doing. I think Martin's just shared in the chat the link to the Gathertown. So I think it will be great to move there and have a conversation. And I have to thank Priscilla already for sharing in English the handbook that she was referring to.